Good morning, everyone. Thank you very much for your attendance for ICAT-EGVE 2022. This is the opening session of this conference. And as you know, ICAT-EGVE is kind of a joint international conference of 22nd International Conference on Artificial Reality and Teleexistence, and also the 27th Eurographics Symposium on Virtual Environment. And this conference is sponsored by VRSJ, Virtual Reality Society of Japan, and also Keio University provides a support for this physical venue. And yeah, this is under incorporation of Eurographics and SMC graph. And also we received some financial support from Yokohama Convention and Visitors Bureau, MIC support. So we would like to thanks for all organizations. So welcome to Keio University. And due to COVID restrictions, we really struggled for these 2 years. And this is our great pleasure to have a physical and hybrid style conference here. And yes, I would like to say thank you very much for your participation for this. This is on behalf of general chairs and program chairs. And let me just briefly introduce chairs. And as you know, Professor Hideo Saito is Honorable General Chair. And my name is Maki Sugimoto from Keio University. And we have organizing chair, Yuta Sugiura, as well. And for the program chairs, we have Professor Uchiyama from NIST and Professor Jamari Nomand. So, yeah. And here we can see the main program of this conference. If you go to the website, you can also see the same program information. So if you have if you think what you should do next, in such a case, please check this information on the website. And we have several keynote talks, and today we have 3 keynote speakers. The first one is Mr. Naoto Kato from Cluster, a virtual environment to have online communication. And the cluster also can be used for the public viewing of this conference. So I hope some users are able to participate from virtual as well. And the second keynote talk is given by Professor Anatol Rekila from India. He will talk about brain-machine interface. And third keynote speaker will be Daito Manabe, a media artist in Japan. He's a really good creator to utilize virtual environment. So to have his talk would be one of the highlights of this conference. And the keynote talks of Mr. Kato and Mr. Manabe will be a joint keynote session with VRST. And on the 2nd December, we also have 2 keynote talks from Professor Yoichi Miyawaki and Professor Kota Minamizawa. And they are very good at analyzing brain activity to have extended embodiment. And Minamizawa sensei is a specialist of telegresistance, so I hope you can enjoy their talk. And last keynote talk in this conference will be from Professor Daisuke Iwai. And his keynote talk is scheduled at the 3rd December, the final date of ICAT. So I hope you can enjoy these keynote talks. And we have several social activities, so I also would like to introduce. Today, we will have a welcome reception in our university. Actually, there is a drinking space in our university. It's called Hub in Keio, and I think you can find the location by just walking something like 3 to 5 minutes. It's quite close. So after closing of today's session, you might have a small break, and then you will go to that place. Actually, the hub is located at the front side of this campus, so you will go back to station side and turn left side. Then you can find a building named Kyosekan, and hub is inside of that building. And for the social activity on the next day, 2nd December, we will go to Yamashita Futo, close to Yamashita Koen, and there is a huge monument, or how can I say? And this is actual dynamic one, and I hope most of you know Gundam. I'm also a big fan of Gundam series, and this is probably I can say this is most famous Japanese animation, at least for Japanese boys. And by looking at this picture, you might not sure about the scale, but this one is a very huge one, kind of real scale of this robot. So I hope, you can see this. And we will arrange a bus for this tour. And the bus will leave from Hiyoshi at 5 p.m. So after finishing keynote talk session, please take the bus. And for the social communication in at the 2nd, we arranged kind of banquet, standing style dinner for you, and it is walking distance from the Gundam factory. So if you walk something like 15 minutes, you can get there by walk. So please check the location. And if you check your tag card, you can find the map information in backside. So please follow that. And some of committee member of APMA will will be invited to another venue. So yeah, please check your location information. It's not the same for you. And for the final day of ICAT, we have a closing keynote talk by Iwai Sensei, and also we have a poster and demo session. So yeah, please consider to join this. And also on this day, we have a collocated workshop, APMA. So yeah, if you have a plan to participate this, you also you can consider to participate this one in various ways. Okay, and I can try to provide a hybrid experience for you. So we will organize all oral sessions by Zoom, and we have a Q&A session associated with Discord. So if you participate via online, you can post questions from Discord. And I hope session chairs will be able to check messages on Discord, and also authors will be. So I hope, yeah, there will be some interactive discussion even in the online. And we have a public stream with YouTube and Cluster. So if you think you can participate in this conference via hybrid style, please consider to utilize this. And the poster and demo session will be organized with Cluster. So yeah, if you want to join this session from online, please utilize Cluster. Okay, that's it. So I hope you can enjoy ICAT-EGVE. Thank you very much for your attention. よろしければ時間となりましたら始めていただきましたら幸いです。よろしくお願いいたします。
Okay. Good morning. Can you hear me?
はい、聞こえております。
Okay, so we will start keynote. So my name is Takafumi Koike from Hosei University and the General Chair of VRST 2022. Okay, so at first, this session, Mr. Naoto Kato from CEO of Cluster will present their keynote. Okay, I will introduce him. Okay, so he studied cosmology and quantum computing at the Faculty of Science of Kyoto University. After dropping out of graduate school, he spent about 3 years as a recluse. In 2015, he founded the VR technology startup Cluster. In 2017, he released Cluster, a VR platform that allows users to hold large-scale virtual events. It has now evolved into a metaverse platform that allows users to not only hold events, but also to talk with friends in their favorite avatars and post online games to play. He was selected as one of the 30 Japanese and 30 who will change the world by the business magazine Forbes Japan. He is the author of Metaverse, Goodbye Atoms Era. Okay, 加藤さん、よろしくお願いします。
Hi. Thank you for introduction. I'm glad to be here, such a great conference. Hi. This talk is, as you can see, bring from the virtual world, something like this. Good morning. And I appreciate the opportunity to talk here and also to be honest, I really a little bit nervous because it's a very extraordinary talk, something like that. And I rarely speak to specialists like yours. Actually, I'm not a scientist, but a business person. So, as you know, some of you, today's audience, may know me, but almost all of you don't know who am I, and this is the first time meeting with many of you. So please allow me introduce myself first. So look at this graph, look at this slide. Okay, I'm not Kato, founder and CEO of Cluster, and our company has about 200 employees, and our Cluster is a startup company developing a virtual platform. And I wrote the book about the metaverse like this. And I know you don't want to read such a small text like this. So I prepare for you to image slide like this. So yeah, when I was in university as a Kyoto University student, my major is not about virtual reality, and I was not computer science. So I studied initially this astrophysics. And that is because I love this anime. So that's Gundam. So it's the greatest anime in the world. So I remember when I was junior high school student, I seriously wanted to work for Anaheim Electronics. Do you know Anaheim Electronics? That's a fictional company within the Gundam story. And that's why I had decided to study astrophysics, but when I was 3 years grade, my friend invited me to another laboratory, and that laboratory studied condensed matter physics. And one of the research topic is this quantum computing. And this sounds very cool, and I, as an anime geek, so it is impossible for me not to be interested in it. So finally, I joined both of the lab, and I wrote the 2 grad papers simultaneously. That's a very hard campus life for me. But as soon as, and finally, I focused on my research topic to quantum computing in the grad school. But as soon as I entered, I ended up quitting out of my grad school. One of the reasons is that that was 10 years ago. And at that time, smartphone market has been growing rapidly, right? So, and I was into programming, and I enjoyed creating some applications, something like utility tools or casual game, something like that. And so I was probably not a scientist, but a creator or a business person. So after quitting my grad school, I spent 3 years as a shatin. So in Japanese, hikikomori. So I I feel very super shut in. And when I talked about this topic, many people ask me something like this question: what do you feel in such a difficult situation? I hear a difficult situation is very interesting, but my answer is very awesome. That feels very great because the internet technology has been growing, so there are almost no inconvenience. So as you know, you can get information, anything you want, and you can get an item. You can purchase anything you want, even if as long as you have the much money, of course. And even you can work from your home if you have the intellectual skill, something like programming. So, but there are only one problem. That problem is not to be able to gather and to meet with others, something like this. So it is true that I am shut in, but that doesn't mean I don't want to communicate with others. So I'm eager to participate in the enthusiastic event like comic market, of course. So and with COVID-19, everyone all over the world experience something like this pain. So with considering how to solve this pain and with hikikomori life, during that hikikomori life, I came across the very impressive and innovative device that is, of course, this VR headset and Oculus Rift. And that was very innovative device. So then when I try it on, I had decided to create a virtual service, something like a user can enter, user can get together in the virtual world and with their avatars and communicate with each other. So that product name is Cluster, and that cluster was called as a metaverse. So today's topic is metaverse. So sorry for longer introduction. This is the starting point of this talk. And metaverse, the term metaverse has become a very big trend. And moreover, metaverse has become a buzzword. So you can often watch this term in the daily news. But when did this trend begin? So look at this graph. This is a Google Trend graph that shows how many search words generated in that designated word and region. And this is a keyword metaverse, and the region is worldwide. And you can see the number of searching has been growing rapidly since just 1 year. And this trigger is obviously him, Mark Zuckerberg. And he is the CEO of former Facebook and now Meta. And he declared just 1 year ago that he aimed to be the metaverse company. And after his declaration, a lot of companies all over the world, like big tech company, Google or Microsoft or Facebook, NVIDIA, they said that they are going for the metaverse. That's a very big wave. And by the way, the concept of the metaverse is when did it appear? And as you know, that was 30 years ago. This one. So, Snow Crash, written by Neil Stephenson and published in 1992. I think today's audience knows much more than I do. So I suppose I don't know how to I don't need to introduce this in detail, but I heard that the term of metaverse itself has existed before this novel, and there are some novels and films to deal with something like virtual world, but this it is from this novel that the term metaverse is used as a current context. And I know I use the metaverse, the term metaverse a lot, but so I guess it is a good time, it is a time to answer this question. What is a metaverse? And this is a very difficult question and a very essential question. Everyone asked this question gives totally different answer, literally totally different. It's very interesting, but that is because the term metaverse has no clear definition, as you know. So this term has become a very useful term for the business person, because if its product uses internet, that this is in metaverse and that is metaverse, everything is metaverse. So that's a very useful term. And I know that is a nonsense to define this term, but I believe it is useful to share the concept of the metaverse. What is a metaverse? And I think this is a good for us, for the consensus. Metaverse is the age for humanity to live in the world created by computers. And this concept is inevitable for all business persons and to agree with. And you can see left one is Ready Player One, directed by Steven Spielberg. That's a great movie. And right one is Ryuto Sobakasu no Hime. That in English name is Belle. That also the main character's name. And that is a Japanese anime published in 2021 and directed by Hosoda Mamoru. And that is a very, I think, the very good consensus for today's audience. And I also have to clear this topic and clear of my stance, and that is this: metaverse and Web3 has nothing to do with each other. Totally nothing, 0%. It's a very important thing. I emphasize on this because a lot of cryptocurrency business person mix them up on purpose. And metaverse is and some experts tend to say that metaverse and Web3 have a little bit great chemistry among it, but I say that is 0%. But that is interesting architecture. They are similar for the architecture, something like this. Metaverse and Web3 is ideology, in my opinion. So they can. I think you can not show the metaverse is actually is. So 3D CG or VR AR is not a metaverse. So that's an implementation of metaverse. Metaverse ideology is something like this. So freedom from materials or world created by computer. And the similar to metaverse, Web3 is also ideology. Web3's ideology is, as you know, something like that. Decentralized society and come back power to creators. So blockchain is not a Web3, and also NFT is not a Web3. That's an implementation of Web3. So I talked a lot from here, but I think deeply, what should I talk today? And I came to the conclusion that it is very good for us to put our product cluster on the main topic. So that is why, that is because our product cluster is the largest virtual platform in Japan, and that's very informative for you. So I want to talk about, at first, something like this. I want you to know what can you do with cluster. And then I'd like to talk about our business model. And after that, this is a very interesting point. What kind of users use this platform? And finally, I want to talk about the future of the metaverse and our product. So let's begin with business of cluster. So look at this video. Wait a sec. Oh, wait a sec. I back to the slide, so wait a second. Yeah. So that is a promotional video of Cluster. So Cluster is a virtual platform, something like you can imagine when you hear the term metaverse. And users can upload their avatar on a platform and get together with their avatars, something like this. And we are the largest metaverse platform in Japan. And users can enter this virtual platform with their VR headset. And I asked a lot about should I use VR headset? But of course not. There is no need to do that. We support not only VR headset, but also smartphone. and PC. So I believe today's audience have everyone have the smartphone, so you can download cluster application with the mobile store. So then, and you can enter this virtual world. So please wait. I'll be waiting. So, and most of you may want to know about our business model. So I will talk business model about first. We have two large business divisions, platform and enterprise. And enterprise division, this right one is enterprise works for the company customer, corporate customers who want to use something like this virtual system. And with COVID-19 and the metaverse trend, a lot of such a need has been growing rapidly. And we managed anything and everything. So we provide producing and planning and creating and running actual event. And this enterprise division makes a huge profit. So we can use that profit to the platform division. And in this platform division, as a platform, we provide our system to every individual user for free and for living in the virtual world. So platform division has not yet to be monetized, but in order to creating the ideal metaverse platform, we invested in it now. And when I asked about what is the best feature of cluster, I would answer that we are the #1 virtual event company, literally, but #1. So in this year, we provide over 160 virtual event, virtual corporate event in a year. So certainly there are some virtual event company and there are some social VR platform, but almost all of them except us can hold the corporate virtual event just a few or dozen event a year. So I feel that's a little insane to hold 160 virtual corporate event in a year, because it's a one and a couple of days. So that's very insane. So let's watch some example, something like this. So we recreate the virtual Shibuya. So virtual crossing, Shibuya crossing is a very famous location globally, and we recreated it. And I can show you the video. So wait a little bit. Something like this. So this project is officially created, and this project very often featured by television. So some of you may know this project, and in this project we collaborate with Kokak Kidotai, something like that. So So I love this, but Kokaki in English name, I think the Ghost in the Shell is my love anime. And so, by the way, you can see the blue little bird, and that is my avatar and my original form. And I can change it right now, something like this. Wait a second. Here, something like this. This is the original form of me. I can transform something like this. And this is a very powerful feature of metaverse. So you can be someone and something you want to be. And wait a second. I have to back to my slide. So another example is like this. So we recreated the Disney game in the virtual. So this is a Twisted Wonderland for virtual Halloween event. And users can enter for the Disney game. And this game is originally 2D game. So a lot of fun is very enjoyed for enthusiastically. And another example here is here. So we create the virtual theme park of Pokemon. And I can show the video of this. Something like this. So in the COVID-19, a lot of real theme park has limited to the number of visitors. So it is very meaningful project. And so from children to adults, a lot of people, a lot of users enjoy this theme park, something like that. So we have a lot of track record about the IP virtual event. So we have received many jobs, many works from the government. We create the Virtual Japan Pavilion for the Ministry of Environment like this. And another example is here. As you know, Osaka Kansai Japan Expo will be held in 2025 in Osaka. And in Japanese, this project was called Banpaku. And Banpaku decided to use Cluster as a virtual venue. So officially, so for preparation for that, Virtual Osaka was pre-opened last year. And a lot of virtual events are held in this Virtual Osaka, something like this M1 Grand Prix. Or another example is here. We are now used in elections. So liberal democratic parties made their virtual speech in Cluster, something like this. And you can see Kono Taro-san and the Ministry of Digital Agency. So, and he tried the virtual head mount display like this, and he manipulates his avatar. And we also used by many universities. So something like this. You can see Tokyo University, the University of Tokyo and Kyoto University like this. And we are used more than 40 universities, and they are often used as a entrance ceremony or graduate ceremony, and a class or festival or something like research conference, something like today. And total number of visitors has exceeded 50 million. So from now on, we talked about the business of cluster. So I will talk about the people living in the virtual world. So I believe this section is the most exciting and most interesting part of this talk. So let's look at this video. Wait a second. This is a video. You can see how our product is used. So some user ride vehicles, or some user enjoy the virtual conference, virtual concert, or play games, or chatting with a friend in the coffee shop. And that is a very ordinary situation of the metaverse. And I have to emphasize on that this video, in this video, every experience is created by users. So creator is created this contents, everything. So to speak, user-generated contents platform. So it's a very important point of the metaverse. So let's look back the slide. So in cluster, we have unique and large communities. And many of you may think that the main use case of cluster is something like this, play games. But that's not correct. The many users use this virtual world, something like this. This one, this left upper side of image, chatting with their friend. And in this image, a lot of users in the virtual during beautiful bar, and I think this word is used by creator, and it's a very normal, it's a very ordinary situation for virtual residents. So it is helpful for you to understand something like this. So please imagine the family restaurant later at night. And in that family restaurant, young people tend to get together with their friend and chatting with their friend and drink a juice at the drink bar, something like that. And people in the virtual lives in the virtual world like this do the very similar things in virtual. And when you learn how to create a virtual world and how to create the gimmick of the virtual world, you can create a lot more complicated thing. So some of users play something like mahjong, or some user enjoys like DJ concert like this. So after all, metaverse is a social experience. So a lot of users and so in metaverse, something like dating or breaking happen very frequently, very frequently. That's very normal. So when I talk about this relationship, social relationship in the virtual world, many of you wonder if this, if the real girl is used this virtual girl, but as you imagine, it's in the most case that is no. So there is very ordinary, that is natural for men to use female avatar. And of course, on the contrary, this is very natural for women to use male avatar, something like this. And so it is very ordinary for them to have a same sexual relationship in virtual. But I have to emphasize that that is not a matter of good or bad. So it is the sign about the metaverse to create a very original culture to allow something like this diverse relationship. So as I said, that's not a matter of good or bad. So such a diverse world, in cluster, over 44,000 words are there, or something like this. Wait a sec. You can see that video. Something like that. We pick up the some user-generated words, something like that, and you can see the very beautiful aquarium or the hotel, virtual hotel. This is a very important and strong point of the metaverse. And I think this one is a very metaverse-like world because a user can jump into the sky with zero gravity like this. And also you can create something like this beautiful virtual world. And of course, you can create something like this fantasy, very huge fantasy world. So this is very important point. The creativity is the essence of the metaverse. Okay. Wait a second. I have to back to the slides, something like that. Okay, and Cluster has a lot of feature of virtual event, because Cluster has started as a virtual event company like that. So in Cluster, user-created event is very popular. So let's look a little example. Sorry, wait a sec. So you can see the video, something like that. So recently, the tracking, body tracking device, the cost has been very decreasing. So a lot of users can hold something like this event. So breaking dance party, or something like this, the radio dance party. And wait a second. In the cluster, show the video is very complicated. Okay. So I think when I think, or many of you may think that creator have to get a special skill to create something like this beautiful world or great world, but that's to be honest, it's a little true for some aspect, but I think that was I want not to make the metaverse something like harsh world. So creating is very difficult, but I want to get them very easy. So Cluster provides two ways to create the virtual world. If you use this hard type creating tool named Cluster Creator Kit, creators with PC and be installing game engine, especially Unity, user can create much more complicated world. But we provide something like this easy type of creating tool and named Worldcraft and support for PC, smartphone, and VR, every platform. And you can watch this video. Wait a second. Sorry, that sound is very big. And so you can use you can create a virtual world with Worldcraft, so very easy way. Everything you have to do is create, put the virtual item on the virtual world. So wait a second, I'm back to the slide. It takes very time to back. Sorry to wait. And additionally, we provide an avatar making system named Avatar Maker, something like this. So that makes users allow to create their own avatar easy. And of course, why cluster existed because creator. So cluster is not a content creator, but a platformer. And any platformer can exist that stand alone. So creator is very important. And that's why we want to, and we have to create the system, something like creator can make money with selling their virtual item. So that's why for the first step, we provide a virtual Worldcraft store at the last September. So I'll show you the video. So this video capture is of my using Worldcraft store, and everything in this capture created by our cluster's user. So user can sell their virtual item on the store, and everyone uses this craft item store. And if you are interested in it, you can try them on something like this. And of course, you can purchase the item with cluster coin. And I have to say that, insist that cluster coin is not a cryptocurrency. We use no blockchain technology. So, and of course, so technically, our cluster coin is something like prepaid point, like Rakuten point. Oh, wait a second. I'll back to the slide. So I believe there are a lot of potential of metaverse, and I think so. Metaverse make everyone to open their world. So we do some project for the future to expand the possibility of the humanity like this. For example, I believe that the metaverse would be useful for children's education. So we collaborate with Ready, that is a digital educational facility for children. And children create the virtual world in the virtual experience in the virtual world, and they also children collaborate with their friend, and I believe that makes the very natural sense of creating or natural sense of living in the virtual world. So I would not be, I suppose it would not be called them as a digital nature, but they would be called virtual nature in the near future. And another example is here. So we started Cluster Metaverse Lab like this. One of the very important point of the metaverse is everything would be digitalized, something like this. So in the digital era, IT era, we use digital technology, but in the metaverse era, we live in the metaverse as a virtual humanity. So everything is digitalized, and that means every data would be storable and computable. So that is very essential point of the metaverse. And actually, our product cluster stored every data in the cloud storage. So today, I'm in this virtual world. So my motion data or voice data, something like this, is automatically stored in the cloud storage. And that's why and moreover, we have the ability to reconstruct all of the experience, designated time and location. That's very powerful. And so reconstructable means computational, calculable. And calculable means we can use machine learning here. So that's why we established a research institute. That name is Metaverse Lab, like this. And we can use, we would use the virtual data for the research. And Metaverse Lab's goal is realize a lifestyle free from the mass. And Metaverse Lab's research area is something like this. The first area is computer vision. So of course, Metaverse and cluster, including cluster, is user-generated experience. So a lot of 3D content are uploaded to the cluster. And I think this data would be useful to update experience in the Metaverse. And the second area is HCI, human-computer interaction. So large number of users would helpful to do the experimental research about the human-computer interaction. And finally, I believe it is inevitable for us to create a metaverse future. We have to research about the brain. So third final area of our laboratory is brain-machine interface. And actually, at now, we are collaborate with 2 laboratories. So Inami Lab is a human-computer interaction laboratories at the University of Tokyo, and Kamitani Labs, and that's a brain-machine interface laboratories in Kyoto University. And of course, we would be happy if collaborate with a lot of laboratories. So please feel free to message to me if you are interested in about our original unique data or our platform. So I'll be waiting for your message. So wait a second. Since I have been talking about a specific topic, so let's move on to the abstract topic. So I took too long from here, so I need to a little bit hurry. So as I said before, the term metaverse has become a useful word. So that is useful for industries. Many companies in these industries listed here said that they are going for the metaverse. And of course, every industry has its own aims. The gaming industry want to be a life infrastructure, and the social media industry want to get more long time attention. And of course, the VR and AR industry want to get more long time, and they want to be used by late majorities. And cryptocurrency industry, they want to increase the value of cryptocurrencies. And finally, semiconductor industries want to increase its need for itself. And it is that we think of the metaverse as a buzzword, but we don't have to overlook the increase in internet population at the background. The internet population has reached 5 billion here. but still 3 billion people are left. And right graph indicate that data traffic globally. It's obvious that mobile data traffic has grown rapidly. But interestingly, wired internet data traffic has also been growing rapidly. So it has roughly tripled over the past 5 years. And it can be said that I think, in my opinion, digitalized will be more accelerated. So this huge trend is behind the metaverse trend. Under this trend, what will happen to us in the near future, 10 or 20 years from now? So let's look at this video. So there are many aspects when we talk about the future. But for now, I picked up a very impressive video from Twitter. So I guess many of you watched this video in Twitter. And I guess this video shows Echu Diamond Station. And surprisingly, this video is running by Unreal Engine 5. So that's not a real video, but a virtual video. So it's not a real-time rendering, but a high-resolution render, around 7 frames per second. But this video creator said that he could run in the real time and 30 to 50 FPS, but the image quality is worse. But I think this shows us the future. It would be hard to distinguish between the real and the virtual, at least in terms of virtual information. So in such a future, we would face a question like this. Wait a second, I have to return to the slide. So I have to answer this question. So is it possible to calculate everything in the world? So it's very attractive question. So but the answer is no. So it was proven that simulating or calculating everything in the real world is NP hard. So it seems no chance for the current computational architecture. But we should ask something like this question. Do we have to calculate everything in the world? So this is a good question. And of course, not. So we consider everything. If we consider everything, even 1 kilogram of rock, something like this image, its amount of information 10 to the 20th power of atom. The amount of information will become enormous, something like this, 10 to 27th power of bit. So compared to the DNA of all human beings, that I guess you feel this is a counterintuitive result, something like this. So just a 1 kilogram rock is complicated, something like this. It's counterintuitive, but it is correct. It is right. And when we think about it, so everything in the metaverse is deformed. So there is no need to calculate everything. In general, we never use precise information about atom in the rock, something like this. So actually, in games, we simulate a rock with polygon or texture and another information. So that's why the ordinary data size of rock are around a few kilobytes. So after all, there is no need to calculate everything. And when we think about it, everything in the metaverse is deformed. So the metaverse deformed not only visual data, but also other data, something like motion, like this, or voice and emotion, etc. So the essence of the metaverse seems to be deformed. So deforming is an intellectual activity. So you can see the face of this image. And of course, you can see face. So not a word or specific character. In Japanese, heno moheji. So, but you can see this image as a face. So that is because your intellectual brain works. So actually, your brain deformed everything in this world. So in that sense, I think our brain is the closest system of the ideal metaverse, like this. So in your imagination, you can create anything you want. Of course, and you can be anything you want to be. So the only problem is that there are no others in our brain. After all, I believe, in my opinion, the ideal metaverse system would be like this. So what do you think? So that's the end of my presentation. Thank you.
Thank you, Mr. Kato. Do you have any question or comment from EGVE2000 venue? Okay. Is there any question from ICAT venue?
質問がある方、挙手していただければマイクを回します。あと、Discord でも Q&A 受け付けております。If you have a question, you can post on Discord, and if you raise your hand, I can hand a microphone to you.
Hello. Thank you for your presentation. I was curious, what would you consider the best use case of brain activity in this metaverse world?
Okay, thank you for your question. You mean brain activity? What do you mean?
I think on one of your slides, the aim 3 was research on brain activity and cyberspace together. So I was just curious what you personally think might be a very interesting use case if brain activity was incorporated into Cluster or another metaverse-like platform.
So with collaborated laboratory, Kamitani Lab, we aim to reconstruct the image of the brain and put out of the virtual world. So if you can imagine when your brain like the chair, you can output from your brain like this. So that's a very great and powerful use case for the brain to the metaverse. And that's an ideal metaverse and brain-machine interface future.
Okay, thank you.
Yes, sure. Okay, so I have a one question. Discord@VRSD. So can we fly in the cluster world? It will be nice for pointing somewhere of the presentation slide.
Sorry, what is the question? I can hear that.
Okay, so
can we fly? Okay.
yeah.
The answer is yes. We don't provide a flying feature for we do not provide a default feature, but users can create the gimmick for flying, something like airplane or something like that. So you can fly the virtual world very freely.
Okay, thank you.
Yeah, thank you. I mean, we're in a world where there are more non-concern about climate change stuff and all of those environmental questions. So I was wondering, how do you plan to, well, reduce the energy consumption of such a virtual system?
That's a difficult question. I think, in my opinion, using a metaverse system is relatively reduce the energy consumption on the contrary of the real world. So, but that's a little difficult question. So.
Okay,
so I'm not confident that I can answer. But I'd like to answer your question. So please let me answer individually with Discord. Okay. Thank you.
Well, sure. Thanks for your question.
Okay, so and one question from Discord. So you mentioned the brain-machine interface. So do you have any examples or ideas of medical applications?
Medical application. So at first, the first use case of brain-machine interface to the metaverse is in the medical application. But I don't think that's not a medical application. That's very difficult. So to be honest, our product metaverse cluster is not a utility tools, but interface or enterprise entertainment field. So I think a little difficult for use medical. So okay, then let's discuss with us. Thank you.
Is there any question from VRST venue? Nothing. Okay. Do you have any question from ICAT venue?
Thank you. It seems that's all. Thank you.
One question from VRST.
Hello. Thank you for the inspiring and very stimulating talk. And I'd like to ask about, in your definition of metaverse, so you emphasize of being completely digital. But there is another keyword like mixed reality or cross reality, which connects virtual and also real. And also in that case, there is physical conditions which are not removed, still exists. So what do you think of connecting such a world and the relation between metaverse and your platform and such a mixed reality or cross reality techniques?
Thank you. To be honest, I don't understand mixed reality is. But I feel that the same thing of mixed reality and virtual reality and augmented, but not a mixed reality is the same as augmented reality. That's it's it's in my opinion, but and cross reality is I don't know that about that concept, and I can understand the cross reality. But so I talk about the AR and VR, augmented reality and virtual reality relationship. That's a little bit. I believe that a good chemical about that two of them, but at this time there are nothing, totally nothing about the relation. Disappointingly, so that's a. So in my opinion, but it is just our just our opinion. I like the pure virtual experience, but this is a ideology or standard of the individual. So that preferable. It's a matter of preparation. So that's a is that the answer of your question? Okay.
Yeah. Thank you. Yeah, I sensed your opinion, and yeah, you're now what you're thinking and what you're now advancing. Yeah, thank you.
Okay, so now it's a time to close. It's a close.
Opportunity to the great conference. Thank you.
加藤さん、小池先生、Thank you so much.
Thank you. So, okay, so, では。Okay, so, じゃあ、すみません、杉本先生、ありがとうございました。こちらの方、退出、Zoom の方切らせていただきたいと思います。Thank you.
ありがとうございました。失礼いたします。Okay, yeah, the keynote talk one is over, and sorry, we have a little delay, so I would like to start the next session, keynote talk 2 from Professor Anatol Rekila at 11:25. So you have something like 7 minutes. ちなみに日本人の方にちょっとトイレのところに、教員専用という記載がありますが、シンポジウムの参加している方は特に気にせずに普通に使っていただいて大丈夫ですので、遠慮なくご使用ください。
Okay, I'm very happy to welcome Dr. Anatole EGVE. He's a research director at INRIA in Rennes, in France. You probably know some of his work on pseudo-haptics. He's very famous for this, and also for work on BCI and, of course, VR and in 3D interaction. Today he's going to talk about BCI and whether it's going to be the future of extended reality or not.
Thank you very much for the introduction, Jean-Marie. And thank you for the invitation, organizers of ICAT and EGVE. It's really a pleasure to be here back in Japan after the great edition of IEEE VR in Osaka a few years ago. It's really a pleasure to present some kind of historical overview of our research activity on brain-computer interface. And I will start from the very beginning, and I can go back to my own childhood, and this little child dream that we probably all had once, being able to control something remotely using your brain. And maybe I'm sure that you tried when you were a kid to concentrate on something, trying to lift this object by the power of your thought. That was the case for me, especially after seeing this movie. I remember very, very precisely, actually. I was 8-year-old in 1980. When I had the chance to see this movie, The Empire Strikes Back, in a cinema room, in a movie theater, with my grandfather, the two of us were watching this movie, and I was really fascinated and deeply marked by this movie. For instance, this sequence, very famous in the movie, where the hero, Luke Skywalker, is trying to lift a spaceship by the power of the Force, the power of his brain, under the advices of Master Yoda. And I kept this, I guess I kept this sequence in my memory for a very long time. And, but also in this movie, there was another sequence, or maybe not in this movie, or maybe in another one. We have probably Star Wars fans in the room, and they can tell me if it was in Empire Strikes Back or if it was in the first episode. Do you remember? No? Okay. No. Not that many Star Wars fans in the room. Anyway, there was this augmented reality chessboard where the pawns are actually augmented reality characters. And also, I definitely wanted to have one day this kind of toy on my table. And that probably also motivated me to start research actually in the field of virtual reality. I started a bit more than 20 years ago a research activity on augmented and virtual reality. And up to now, I could explore different kinds of topics. I worked in my team with a group of excellent colleagues. Some of them are here in the room. We could work on haptics, on avatar, 3D user interface. These are examples of more or less recent works of our team. For instance, this avatarization in augmented reality by displaying, for instance, virtual hands robotic hand at the level of your real hand using optical see-through, playing with virtual embodiment and avatar connection with such kind of six-finger illusion that we can induce in virtual reality, or working on haptics, for instance, here with playing with visual effects, visual haptics effects that we call pseudo-haptics, for instance, displaying texture sensation on a tablet using effects at the level of the cursor, or here working on more core haptic technology, like this encounter type haptics where you grasp a virtual object, you can release it, and you can feel actually this virtual object in your hand using an encounter type display here, which is bringing the tangible interface in your hand when you're grasping the virtual object. So we have been playing around with all these different research paths for several decades now. But so how BCI came into the play? Actually, it was in 2003. So I was a young INRIA researcher starting my research career now after my PhD. And I was totally not aware about BCI technologies. And I was contacted by a PhD student in the US, Marco Congedo. He was finishing his PhD and was looking for a postdoc. He was working on neurofeedback. So neurofeedback is a way, a method to learn to control progressively your brain activity by having and gaining a feedback about your brain activity. So you visualize a brain wave, and progressively you learn to control this brain wave by looking at it. So maybe you are familiar with this technique. I was totally unaware about this technique at this period in 2003. Marco was working on this using electroencephalography, EEG, and actually he was very interested in virtual reality technologies. That's why he was contacting us from the US, being an Italian researcher. And so he sent me an email and a research project for his postdoc, in which he wrote this sentence: I believe that these two fields, virtual environments and neurofeedback, may merge into each other for the benefit of both, in April 2003. And then I said, wow, that's a really cool idea. So maybe we could have these systems where you record EEG, you analyze the EEG data, you detect some brain activity patterns, and you can translate this into a command to control a system. Wow, let's do that. I can make a patent on this. But actually, this was existing for 30 years already. So I was quite frustrated at this time. I discovered this actually a few weeks after accepting him as a postdoc. And I was a bit disappointed because maybe it also happened to you. You have a great idea and you just notice that it is existing for 30 years. And so I was observing what was done in BCI at this time. It's been existing for a very long time, actually. BCI old-timers start with Hans Berger in the beginning of the previous century, 1929. He published the first EEG recordings and EEG signals, German researchers. And you can even see in this first and very emotive, actually, it's really nice to see this very first recording of EEG signals on the scalp of a human being. You see here that when the person, it's a recording of EEG signals when a person is closing the eyes and opening the eyes. Closing the eyes, opening the eyes. And what happens when your eyes are closed is that you see appearing directly in the electroencephalography signals, you see this oscillation here appearing when you close the eyes in every human being brain. And this is called the alpha brainwave. It's around 10 hertz oscillation, which is appearing in your brainwaves when you're closing your eyes or when you get a lot of relaxation and you get calm. And in 1960s, there is a great paper by Edmond Dewan, I think it's in a Nature journal, which is actually showing here this setup and this prototype. It's dating from the 60s, this video, where somebody is actually sending message by Morse code, long beep, short beep, using this alpha brainwave. So if you increase the brainwave, the lamp gets on. If you decrease the brainwave, the alpha brainwave, the lamps get turned off. And by using this system, this very simple system, this person could send messages using only brain activity. So actually the concepts are pretty old. Even the first prototypes are pretty old. And today what we are seeing often at television, in demonstration, it's basically exactly the same thing. So the fundamental concepts have been existing for a very long time. In 1970s, at UCLA, Jacques Vidal, maybe you are aware about it also, a Belgian researcher who moved to UCLA, coined the term brain-computer interface and set up the first BCI laboratory. So again, it's dating from a certain time now. So looking at this, our strategy in Rennes was confronted to this historical background, and we decided to adapt a bit our strategy and to focus on connecting brain-computer interface technology with virtual reality technologies together. In our opinion, this was pretty new, although this was a kind of science fiction again. If you remember the first Matrix movie, it's very close, actually, to what we were intending to do. You are somehow connecting directly your brain and your nervous system to some kind of virtual reality simulation, like in Matrix. But if you analyze a little bit the system, of course, it's going to be slightly different. We are not going to hijack your system, your perceptual and cognitive system. In the science fiction, it's potentially very intrusive systems, like in Matrix, where you have this hijack here, because you are hacking the brain in both ways somehow. You are hacking it in because you are trying to replace the information coming from your sensory sensors to the central nervous system. You are trying to replace what your body is actually sensing by something else. And you are also hacking it in the other way. So you are trying to intercept the information coming from your central nervous system, which is sent to the muscles, and send another command, for instance, to launch this information into the matrix to be able to drive the motor actions of your avatar in the matrix. And this is, of course, very intrusive because you are connected in different parts of your body, probably in the brain, at different levels in your body. So in real life, clearly, we are not going to do the same. And we are considering here that for hacking in, we are rather using virtual reality to provide the fake sensory stimulation, but it's an external stimulation, it's not an internal stimulation. I hope I'm clear. So we are using VR as the source of sensory stimulation, and actually we are using an input device called the brain-computer interface to measure your brain activity in order to send the command to the system. Okay, so the scheme is a little bit different, hopefully, for a while. Of course, for the BCI, you can have some intrusive system, invasive system here, where the electrodes are implanted in the brain, I mean, inside, under the scalp. But it's pretty rare today, of course. It's often restricted to people with strong disabilities. And the early work in connecting BCI and VR, so in my opinion, but I'd be happy to hear your feedback about it, this is the first paper I found on connecting BCI and virtual reality. It corresponds to the work of Jessica Bayliss at Rochester Institute of Technology, early 2000s, working at first with Dana Ballard at Texas, at Austin, Texas at Austin University. In the beginning of the years 2000, Jessica and Dana, they already tested the compatibility of the two devices and showed that you could use, actually you could elicit proper EEG signals and neuromarkers in virtual reality first, and then after they use a BCI here to control a virtual apartment, to control different aspects of the virtual apartment. And this is, in my opinion, the first paper connecting these two systems at the very same moment where we tried to address this field and enter this field. So at INRIA, we started in 2005, 2006. We had the chance to recruit an excellent PhD student at this moment, Fabien Lotte, who has become now one of the key leaders in the field in brain-computer interface, especially on this topic. He's now a director of research at INRIA Bordeaux. And with Fabien, we really explored this connection between virtual reality and brain-computer interface together. And this is the first setup that we developed at INRIA. And interestingly, you will recognize the reference. But for the Star Wars fans, it's the dark side version. Because it's not Master Yoda, it's Darth Vader here training you. That's a little joke here. So in this very first setup, you had an old EEG setup, very tedious to install, and you are supposed to lift this virtual spaceship using only your brainwave. And in this case, what we are using is the motor activity of your motor cortex at the level of the feet, at the top of your brain here. So you have to concentrate and imagine a motion of your feet to lift the virtual spaceship. And we are using also stereoscopic wall. We didn't have HMD as the ones we have today available, so we are using this big immersive wall. And in stereoscopic viewing, you could get immersed in this very basic and simple scene and try to train to become a Jedi. Okay, a bit later on, we try to improve the system. Here it's a virtual visit of a museum with 3 classes, with 3 different actions, imagination of left hand movement, imagination of right hand movement, imagination of feet to go left, right, or move or advance in the simulation. And we tried different user interface, different shared control approach to improve the navigation and go faster in the virtual museum visit. After these first attempts in 2008, with the few groups who were working on BCI and VR, there were, let's say, 5 or 10 groups working on this topic in these years, we decided to collectively try to address the field and identify the different research challenges in connection between BCI and virtual reality. So this was done with Richard Reilly in Ireland, Robert Lieb in Graz University, pioneers of the field, and also Michitaka Hirose from University of Tokyo. There were researchers at University of Tokyo working on this topic, and Mel Slater from UCL. And so we tried to derive the big challenges. We are presenting different systems. This is actually a picture taken at University of Tokyo in 2007, I guess, connecting BCI and virtual environments. And this one is also from Graz University with disabled people inside a cave trying to advance in a virtual street using a BCI. And we identify a few research challenges. And what is interesting is that these challenges remain more or less exactly the same today. So it's a very long run, and it also shows that we advance very slowly in this field. Basically, we identify that we clearly need to improve the hardware and adapt the hardware to the user environment, which is not the case today. It's very bulky to have an EEG setup at home. We need to better understand the brain cognitive mechanisms, the neurophysiology of the brain, the neuroscience behind these neuromarkers, especially in the context of virtual reality. Of course, it's a huge challenge to signal processing, to process the EEG signals. And there are lots of research on this topic, of course. And then we also quite early identified the need to bring BCI into HCI. And that very few researchers from HCI were working on BCI. Most of the researchers were coming from signal processing or EEG hardware, and they were not aware about all the important methodology of HCI in order to make a system really acceptable and usable by people. and bringing BCI into real-life situation, going in the wild, out of the lab to confront to the real users, especially for patients, to do, for instance, proper clinical studies. And these challenges actually remain quite up to date today. For instance, for the hardware requirements, if you look at the current hardware and what we should get in order to get these systems used by video game players on a daily basis, that's something that we did in 2009, 2010 with the Ubisoft company in France. We tried to address the requirements of what should be an EEG headset in the future for the video game industry. And we came up with a long list of requirements, like easy to put on, adapted to various sizes, simple to clean, with headphones, compatible with other equipments, wireless, etc., etc., robust to noise. For instance, video game players, they like to chew a chewing gum, and it's definitely killing the EEG signals. So long duration of use, small calibration time, and so on and so on. So we are really far from this at the moment. So we said, well, it's a very good and trendy topic for research. We have lots of stuff to do, and I would encourage the community to work on it. There are lots of things we can do with BCI and virtual reality, but several things you should know before starting research on VR and BCI is that on the positive side, it's a very open and promising topic, of course, since there is a lot of space here. The technology is actually already available, and there are some low-cost solutions like OpenBCI, OpenEEG, OpenVibe. These are tools that you can afford for very few costs. Impressive prototypes already exist, and they can be a source of inspiration. I'll show some of them right after. And BCI-based interaction is kind of unique if you have tried it. It's kind of unique to imagine that it's only your brain activity which is controlling or interacting with the system at the moment. And a very good, in my opinion, point here is that it's strongly pluridisciplinary, and it forces you to connect and exchange with other communities, discussing with neuroscientists, signal processing experts, clinical experts. Now, on the negative side, hardware sucks, clearly. It's really painful. I mean, it's very complicated to install an EEG setup. Patients or participants have to wash their head after using a BCI, so that's something that usually you are not confronted in VR. BCI is working, but not always, and it's difficult to know why. So it's when you are confronted to a system which is not operational, how do you know where does it come from? Signal processing is very challenging, so when you are coming from computer science, you are not a signal processing expert, you are not a neuroscience expert, so that's the downside of the pluridisciplinarity. And user studies are clearly tedious. It takes a long time to install the EEG setup, to check the impedance, to explain to the participants, to learn and train to the system. It can be really long, and participants, sometimes they never come back in your lab. And papers can be difficult to be accepted, actually, in the end. That's another problem, because, for instance, for a long time, if you would like to publish a paper at CAI on BCI, they would say, but why don't you use a gaze tracking system instead of this system? It's completely crappy. So it's difficult to make advance the field when you have, of course, other tools which are more efficient at the moment. Okay, I hope you are not too discouraged right now. Because actually there are lots of stuff to do, and in our team at Hybrid at INRIA Rennes, our objective that we defined together is to study human-computer interaction based on BCI and virtual reality, and we could identify several potential topics, like studying neuromarkers of the VR user experience, better understanding in your brain what is happening in VR, designing novel BCI-based interaction techniques for VR, and better understanding what happens when you are using a BCI, the BCI user experience. And also developing specific and novel immersive systems, interactive systems for a wide range of applications like medicine, sport, entertainment, and so on. And our approach is to combine these complex technologies and conduct online experiments with participants, not only doing offline signal processing. So let me show you how we started. In 2005, we launched the first French project on BCI called OpenVibe that was focused on BCI for disabled people. So we came up with different tools, different prototypes for disabled people to be able to spell words using their mental activity. And also starting to design virtual environments adapted to BCI, like this little game, soccer game or handball game where you have to score at the left or at the right in VR. This led to an open source software called OpenVibe. I don't know if you are familiar with this software. It's a tool which is open source, free for the BCI research community. It's widely used worldwide. There are lots of projects based on this. And it's actually maintained a lot by our team at INRIA and by other teams at INRIA. And we are continuously supporting our users with this software to promote open science on this topic. The code is quite extended right now. It's quite popular. Here are some figures. We have 1,000 people registered on the forum, lots of citations, and it's a strong effort from us. But if you look in YouTube, made with OpenVibe, you will find lots of different systems, and that's a pleasure for us to see that the software is used by many labs to do a lot of different things, including motor control experiments, artistic performance, control of robots, etc., etc. Right after, and using our software, we started this big project with Ubisoft and the video game companies on testing the potential of BCI for video games. It was a very exciting project with lots of funny prototypes that we designed with video game studios. This is a Nintendo Wii game called Kokoto, which was hacked to introduce BCI commands in it. And using the BCI and the mouse, you can play with this video game to defend the princess in the middle from the enemy coming from the sides. And you have to concentrate on the enemy to kill them. And then with the mouse, you can activate some option and also click on different things in the screens. So it's mixing BCI and mouse. Other examples of research video games that we built in this project are these two basic and simple video games. This is a video game inspired by Space Invaders, where you control this virtual spaceship here to destroy enemy coming from the top. And this is based on a specific pattern which is occurring at the level of your virtual cortex and your visual cortex, sorry, at the back of the head. If you look at these 3 flickering targets here, at the level of the left wing, right wing, and cannon, they are flickering at different frequencies, 5 Hertz, 7 Hertz, 8 Hertz. So if you look at one of these, for instance, the left wing at 5 Hertz, and we look at the electrical activity at the back of your head, if you do a spectral analysis, you will notice a peak at 5 Hertz in your brain. So by identifying the peak in your brain in terms of frequency, we can identify which target you are looking at and launch the corresponding command. Go right, go left, or shoot. And as you see, it's quite fast and it's quite efficient because it's very robust in every people's brain. And this one is also a funny experience. I think it's one of the first multi-user BCI video game published in 2013. And here we had 2 people facing each other. So you have 2 EEG headsets, and it's some kind of mental duel. So you have to think stronger than the other one. And the higher mental activity, the higher your chance to win the game. So it was called Brain Arena. It was a collaborative or competitive BCI-based video game. So now I'm going to dig a little bit more deeper into our research topics, neuromarkers of XR, user experience, BCI-based interaction techniques, better understanding the BCI user experience, and novel interactive systems for medicine, sport, and entertainment. So let's start with the neuromarkers. With different colleagues, we try to elicit and better understand what happens in your brain and what we can find in your brain when you are in VR. So for instance, here we notice what happens in your brain when there is a problem, an issue with the system, like you have a tracking error. You lose the tracking. That's the case here. This object is lost in tracking. And you can notice that there is an interaction error. There is a problem in the interaction. And what is nice is that we can clearly identify this in your brain. It's called an error potential. And that we can use it nearly in real time in single trial classification. So we can probably detect in your brain moments when you detect an error in the system, which could be, for instance, useful to make an undo command, automatic undo command in the system. Also, we work on virtual embodiment and agency toward avatars. And in this very interesting paper too, we were looking at the connection you have with your avatar. So you are doing a motion, your virtual avatar is doing the same motion here. But sometimes the avatar does something different. So imagine you move a finger and the avatar is moving another finger. It's very strange as a situation, and we notice markers in your brain which is activated actually when something happens like this. So when you lose the control of your avatar, when you lose the agency toward your avatar. Interestingly, these neuromarkers corresponds exactly or nearly exactly to the one that is a reference in the literature of schizophrenic patients when they are having experience of an hallucination. So this means that when in VR you lose the control of your virtual body, your brain experiences an hallucination situation. We could apply this approach to sport training using this system here in a cave where we measure the EEG of shooters in an Olympic 10-meter pistol shooting game or training system. And the idea is to find the neuromarkers of a good shooting versus a bad shooting. And after that, to train the sportsman in increasing this neuromarker to get better on the long run at this sport. Regarding the BCI user experience, we try to better understand what it makes and what it feels to control a BCI. And we were interested in different aspects, frustration and cognitive load, for instance, because as you may know, BCI are not very reliable. They make a lot of mistakes. And we were wondering at which level of mistakes you decide to stop using the BCI because it's not exploitable, it's not usable anymore. So we did an experiment. It was pretty funny because actually people were connected with an AG to a system. It was this kind of task here where you have to select a target among 3 flickering targets. If you remember the Space Invader video game, it's exactly the same situation. You have to select one of these targets, it's flickering. And people are strongly concentrated on this task, but actually the EEG headset was not connected. It was one of the rare BCI experiments where people were not actually controlling the system, totally not. And the EEG headset was not connected because we wanted to control the error rate of the system. So we introduced artificially different error rate. 5% of error, 20% of error, 35% of error, and even a situation where you had an artificial fake system of 50% of error. 1 out of 2 trials, you made an error, however you were concentrating. Interestingly, what we notice is that there is, with such BCI systems, the frustration is never going very high. So meaning that people are quite tolerant with respect to this technology. We are quite surprised by this result. Meaning that compared to a keyboard which is working like 50% of the time, you would throw the keyword immediately away. But with the BCI, you are more tolerant. And regarding the cognitive load, often we had the question, can I use the BCI and do something else at the same time? So can I, for instance, answer to the phone and continue to use my BCI? And so we did this experiment where we use an end-back task and we try to measure and assess the cognitive load of a BCI. And we were quite surprised in this 2017 paper at ICAT-EGVE that actually, yes, you can think of something else when using this kind of BCI. So you are supposed to do an end-back task, quite demanding cognitive load, and selecting a virtual target. And interestingly, people were quite successful at it. So it's a bit counterintuitive here. Moving to the next topic, BCI-based interaction techniques. We explore different ways to combine, for instance, BCI with other inputs, like the mouse, but also here the gaze. And we define here techniques and strategy to mix gaze tracking and BCI together. And in this work, we propose a Bayesian-based approach to fuse the different information and input of the user, gaze information, and BCI-based interaction, cerebral activity, into one single selection decision-making process. Well, it was not super successful. Actually, yes, here again, gaze alone is quite sufficient to select. And we didn't find at this stage, in 2016, that EEG signals were improving the quality of the gaze-based selection. But there is room for future work, I guess. More recently, we are very interested in testing novel technology mixing. For instance, this is the first connection between a HoloLens and a BCI, so an augmented reality headset and a BCI system. We did it in 2020, and we showed that it was compatible and feasible to control here a robot with this HoloLens system using this similar overlay of flickering targets to control the advance motion, the rotation to the right, rotation to the left, enabling this here motion of the robot on the ground. And also we studied different kinds of 3D user interface, how to do the layout, how to present the different flickering targets to the user in augmented reality. This led us to these very recent papers where we investigated a smart home application controlled by BCI and augmented reality, still with an HoloLens. And here you have different smart objects like this fan, this lamp, and this television that you are activating remotely using your brain activity and flickering menus overlaid to your environment using a Microsoft HoloLens. So you can here change the channel of the television by selecting the proper key, activate the lamp, activate the fan, all by concentrating on those flickering targets. Another very interesting connection for us was this first connection between BCI and haptics. Haptics is really a topic that we like to develop in our team, and we wanted to test also the compatibility of the two systems. And in this very interesting paper, we showed that we could use BCI to activate haptic guidance and activate force feedback of a guiding during this complex task where you have to achieve this little trajectory, but without touching the walls. And when here the cursor gets blue, it means that you have a high workload, and we're activating a force feedback here, which is sliding and guiding you along the maze. And this cursor becomes white when the workload decreases, and you will notice that it decreases at the end when it's less difficult. So it's a super great proof of concept of using mental workload for activating force feedback and haptics. We use it actually after that in a medical simulator for training surgeons. Here again, the BCI used to measure the mental workload and to activate guidance in this training scenario where you have to insert a needle to detect a tumor in a virtual lever. Continuing on BCI and augmented reality, this is another way to exploit, in my opinion, EEG signals. It's for visualization purpose, for 3D visualization. This is a system that we call mind mirror. So a mirror of your brain. So you look at yourself in the mirror, and interestingly, you see your brain in action in your head. Like this could maybe one day be implemented in any mirror. So you could check what you are thinking at, and you could check also to visualize your brain in action when you are thinking of something. And so we found that it was very efficient, very functional. And the idea behind is to design neurofeedback techniques for the medical field, for people who need to train some brain activity, brain region, using a visualization of their brain activity, going back to the neurofeedback aspect. In this same line of research, we founded a startup company in 2013. It lasted 6 or 7 years. And we put on the market a product for neurofeedback here, based on a tablet, for the concentration and the attention of children suffering from attention deficit disorder. And this was one of the first systems which was deployed at home, proposing different video games based on BCI to increase the attention of these children who have difficulties to stay focused and stay concentrated on a task. And more recently, we started a big project combining EEG and fMRI for improving the resolution and the measuring of brain activity, and progressively introducing XR technology and haptics in it. So in this case, you combine 2 different kinds of imagery techniques, EEG headset, high density, and an fMRI scanner. And here it's again a neurofeedback techniques where you have to control this little cursor here and lift the cursor. On this dimension, it's the EEG neuromarkers. This dimension, the fMRI neuromarkers, meaning that you have to boost your fMRI and boost your EEG to go up. And this is, for us, very promising for stroke patients and depression patients who have ongoing clinical studies trying to see the benefits of combining these 2 techniques for these patients. Okay, few lessons learned after all these works. First of all, I think we should forget about controlling replacing the controller. Lots of people are thinking that the next ultimate input device could be the BCI, and that the BCI ultimately will substitute for the joystick, will substitute for the controller. Forget about it. We are very far from this. And clearly, using a controller or using a keyboard is way, way more efficient than a BCI. And actually, be careful with disabled people in overclaiming these kind of things. I've been receiving regularly some emails from disabled people asking to test and to use the system to replace their accessibility system. And clearly, at the moment, it's not better with a BCI than with traditional accessibility interface that are really, in most cases, very powerful. So we have to be careful about this overclaim potential of the BCI. I believe that it's more promising to try to identify and characterize, like we started to do, the neuromarkers in our field of extended reality, virtual embodiment, agency, good immersion, presence, etc. That's, in my opinion, a very good line of research, better characterizing what happens in your brain when you are immersed in a virtual environment or in augmented reality. Probably let's go passive. Remember this other approach where you monitor the brain and these neuromarkers and you adapt the interaction or the content to the mental state of the user. I think that's very promising. And we have to be creative, inventing novel gameplays and interaction schemes really based on these neuromarkers. I remember in this video game project I was mentioning with Ubisoft, one of the ideas that came out was that we should probably not use the BCI in a tennis game for controlling the racket and the motion of the user. But instead, probably an interesting approach would be to measure the concentration of the player, the attention of the player, and imagine that before the service, before to serve, you have to concentrate like you do in tennis. And if you have a good concentration, then you have more chances to make an ace. But if you are badly concentrated, you will make a double fault. And that's probably going to increase the gameplay in a more interesting way. That was one of the gameplay novel schemes that we could propose here. Then promoting open science seems to us a very important aspect because this field needs to grow, needs to develop, and also to touch a lot of labs, especially for disabled people. And last, let's try to go multimodal. It's even more complex, but we can access a multiple of input of the user for the benefit of a better recognition of the internal state of the user. One example of this is this physiological HMD that we developed 2 years ago with the Beacom Research Institute, in which we could assemble inside one unique setup and unique system a cardiac sensor, an electrodermal sensor, ocular measurements, which is quite classics, but also FNIRS, functional near infrared spectroscopy, all in one and integrated into the same HMD. And with this system, we could show here that we could get an access in a quite precise manner to 4 different levels of mental workload in real time. Here, from low mental workload to high mental workload, and here the classification score for these 4 different levels. Here coming from different sensors and using a deep learning approach. If you're more interested on this topic of affective and cognitive VR, we just released also a TVCG survey about this if you're interested. Okay, for the future now, we are willing to work on continuing this combination of technologies, moving towards native hybrid technologies, mixing, integrating virtual reality, imagery techniques, physiological computing, all in the same systems. I think we are moving toward more and more of these. And there are lots of applications for XR, for health, sport, training, education, of course, entertainment, etc. That's the end of my talk. For the last slide, I wanted to show you, going back to the initial motivation, probably one of the funniest project we had in the team. I could find the money to fund my initial dream of reproducing the sequence on virtual Dagobah with Master Yoda. It was in our cave in Rennes, our big cave with a computer graphist to design some kind of evocative characters reminding Yoda and R2 here. And you are embodied in Luke Skywalker with a brain-computer interface, and you can train yourself to become a Jedi, try to lift the virtual spaceship using motion tracking, 3D spatialized sound, and nice computer graphic effects. That was in 2013. We had a lot of fun with it, but I discovered that unfortunately I'm not a Jedi, but I'm going to try to practice again, and I hope one day I will become one. Okay, thank you for your attention. This concludes my talk. I hope I was on time, and I'm ready to hear your questions. I'll be happy to answer your questions. Thank you.
Thank you very much, Anatole. You check the Discord? Okay. Maybe first, are there some questions in the room? Yes, I'll bring the microphone.
Thank you for your wonderful presentation. I want to inquire, currently or in near future, does this technology brain-computer interface control an image or a video based on users' thinking? If it can, how the accuracy is? Thank you.
Thank you very much for the question. So we try in a very pedagogical way, notably with journalists and with the media. We really try now more and more in the BCI community, at least in France, to avoid to say that we are able to read your thoughts and that we are able with this technology to read what in your dreams, for instance, or in your thought. We are very far from that, very, very far from that. What we are doing is we are reading the cerebral electrical activity, which is a manifestation of your thought, but it's very an electrical manifestation of this activity. And we try to recognize in this cerebral activity some brain patterns that we can use after that, and that we can correlate with some cognitive mechanisms or external stimulations. So we more talk about being able to control or interact directly by means of brain activity. But we never use the term thought or dreams. And I guess we are very far from that. And I don't know when it will be possible, but I'm not sure I will be here to see that. Thank you.
Thank you. Some more questions, maybe?
Thank you for your presentation. I'm curious about future interaction in VR. Do you think all interaction will be conducted only by EEG or EEG with controllers or gaze input?
Yeah, thank you very much for the question. It really goes back to what I was mentioning as the lessons learned. In my opinion, in some cases, it could make sense to control directly with the EEG signals if, for instance, the gameplay is really integrating these signals into something which is fun for the user, for instance, in a video game, where you have to control your brain to become a Jedi. This makes total sense. Now, if you want to substitute a joystick by a BCI, at the moment, it's way less efficient and way less effective, and I suppose that it's not bringing a real added value. So in my opinion, it's more the other option that you are mentioning. It's that we are going to mix, and it's better to mix the BCI and the EEG signals with other inputs from the user and other possibility of actions from the user, and try to better use what we can gain from the EEG signals. And in my opinion, what we could gain is those famous EEG neuromarkers of the XR user experience that we need to better address, better understand and model, and then after exploit properly by proposing interesting interaction schemes. Thank you.
Hi, thank you for your talk. I was interested in whether you have, because it seems to me that you're trying to rather directly interact with objects. Have you also thought about more an indirect interaction for more immersion? Like, I'm coming from games engineering study, and we do a lot of studies about like how immersive things are, and I feel like, especially like with the workload of the user's thoughts, you said that it can already be tracked quite robustly. So I feel like that would be a great thing to, for example, adapt difficulty levels of games to the user's needs. Have you thought about stuff like that?
Yeah, thank you very much for the question. It's clearly the direction that we are taking at the moment. I mean, one of them at least, in which we believe there is a high potential. So indeed, in another follow-up paper, we tried to use and exploit and see that it was possible to adapt, for instance, training scenarios to the workload of somebody. And we believe that this is, for instance, clearly a potential good path to exploit this technology with other technologies, probably, physiological sensing technologies, for adapting the interaction to the internal state of the user or the cognitive state of the user. Yeah, definitely.
Thank you. Some more questions?
Hi, thanks for the presentation. It was very nice. I was wondering, you said, for example, the task where you have these like flickering triangles with different frequencies, that was easy to transfer that sort of between users. Is it generally very hard, like certain tasks, to expect the same things when you like use? Does it make sense? Like when you change users, and like what kind of calibration processes would you need to use?
Yeah, thanks for the question. It's regarding, so there are different BCI paradigms. You can rely on different approach to exploit mental cerebral activity for interaction purpose. Some of these are called endogenous tasks, where you have to, for instance, for motor imagery, you have to generate a mental activity which is detected by the system. And some others, like the SSVP, the flickering targets, it's an external stimulation which is generating a reaction from your brain. So it's two different kinds of BCI-based interaction. The external stimulation one is requiring less calibration and less training because it's a reaction of your brain, some kind of reflex from your brain activity. So less calibration, less training. The other one, where you have to produce, generate a mental activity, requires often more training and is highly variable across individuals. So the figures are not always known, but it's true that there is lots of variability, and calibration is often the case. With the external stimulation one, there are now more and more papers toward maybe not zero calibration, but we said less calibration for the user. So this direction is inducing less calibration.
Thank you for your presentation. And in your presentation, there is a topic about video games. In current video games, there are many inputs simultaneously done. For example, in FPS game, moving a character and rotating a camera and shooting a gun are simultaneously done. So in current BCI, how many inputs can be done simultaneously?
Thanks for the question. That's clearly an issue that you want to consider when you are designing an interface for a user. When we go back to this differentiation I was making between the endogenous BCI and heterogeneous BCI, I mean external and internal approach, where you have this BCI where you have to generate a mental activity. Here the classification score drops rapidly with the number of class and the number of commands. So if you have like 2 commands, it's okay. 3 commands, so 3 different kinds of mental activity you have to generate. The classification score are reducing due to the signal processing techniques. So generally we go up to 3, 4 commands with those endogenous and mental imagery approach, for instance, which is not a lot, right? And with this external stimulation and flickering stimuli, for instance, you can have a lot of this. So for instance, there are keyboards with LEDs flickering at different frequencies, and you can select the key on the keyboard with pretty good classification results, because the accuracy of the detection goes, I mean, you can, if you have 6 Hertz and 6.1 Hertz, you can detect the difference in your brain. So it's very robust, and you can have a lot of different commands in this case. But the drawback is that you have a lot of flickering targets, lots of external stimulation, so it's tiring visually. So there are pros and cons for every approach. One has less commands, but no external stimulation. The other one, more commands, but complex menus.
Okay, maybe one quick last question, quickly. Thank you.
Bonjour. So great talk, very interesting. I was wondering also about this blinking, the triangles and detecting the frequency. I found that very interesting. I didn't know about this approach of using the BCI. I wondered, of course, that's a very easy to detect a pattern, but probably in reality, everything we see, the whole experience, leaves this kind of after image in our brain waves. And so I was wondering if you're using information like this to, like noise cancelling, denoise your other brain waves, or is that too complicated?
In the case of the flickering targets, you really need to have a stable frequency. So things that are flickering with a stable frequency for long duration in real world, you don't have that many situations. Like you can have a neon which is flickering, or when you go to nightclub, there are some flickering things, but it's not always present. So in the real life, you don't have that many opportunities, but still. And actually, one of the good direction, one work that we published and also Microsoft published recently, was that maybe we could use in an ecological way those naturally flickering systems to be integrated in a BCI system. Like if you look at a butterfly, then if you look at one butterfly on other butterfly which is flickering at different frequency, then this could be used in a more ecological way to control things. You can follow one butterfly go in one direction. That's what we did in a previous paper in Presence in like 6 or 7 years ago. You would follow the butterfly. So this could be helpful actually in the real life too in real life inspired scenario. But in the real life, there are not that many situations where you have stable flickering targets you can look at and that will generate these kind of patterns.
I see. So normally if we're looking at just the table, then that won't probably produce something like that. Okay, thanks for the explanation.
Thank you.
Great talk.
Well, let's thank Anatole again very much. He has to leave quite soon, so but unfortunately. But thank you again, Anatole, and thank everyone.
This is the end of the morning session, so please take your lunch. If you want to find a restaurant, you can go to the other side of Hyo Station. Then there are so many places to take your lunch. So yeah, please go there. And the next paper session will start at 1:30 p.m. Thank you.
Okay, welcome back everyone. I hope you had time to have some lunch. We'll start with the first session of the ICAT-EGVE 2022 conference. The first session is on interaction. We'll have 5 papers and we'll start with the one from the EBISC lab and the Université-d'Evry, Université Paris-Saclay in France, presented by Cassandre, which is called Comparing Modalities to Communicate Movement Amplitude During Tool Manipulation in a Shared Learning Virtual Environment.
So, hello everyone. My name is, I don't think it's working. Ça y met? 1, 2, c'est bon. So I will begin. So hello everyone, my name is Cassandre Simon. I'm a PhD student in the EBISC laboratory from Université Paris-Saclay in France. So this work was realized with my PhD supervisor called Sami Rothman and Amin Shelali. And I will introduce you the following study comparing modalities to communicate movement amplitude during tool manipulation in the shared learning virtual environment. So in medicine, students interact with teachers in the early stage of training. It's called mentorship. Mentorship is defined as advice and support offered by more experienced peers. So this mentorship model follows the paradigm see one, do one, and teach one. It's a well-established model for training technical skills in medicine, but it's not really safe and not ethical because they begin to train on a real patient directly. So to overcome this problem, they can use simulators in which students can practice every time they want on different scenarios without hurting the patient. In particular, VR simulators can play an important role in this context by offering immersive experience. But current immersive simulator using VR and using head-mounted display are mostly in an autonomous learning where the students learn by himself. Therefore, we lose the teacher help and guidance. So our research problematic is how to reintroduce the teacher in the loop in immersive virtual simulators. So a little bit state of the art. So in VR, we can use a collaborative virtual environment. Collaborative virtual environment can support teacher-learners interaction in immersive simulators because they allow multiple users working together in the shared immersive space. However, communication in this immersive collaborative virtual environment is different from face-to-face communication. So in fact, in face-to-face communication, the mentorship model often uses the concept of augmented feedback. This augmented feedback is defined as information augmented by a teacher using multimodal heads rather than being received directly for the learner's sense. The augmented feedback depends on the skills to be learned, but also of the availability of the communication modality. So when learning technical skills in medicine, the augmented feedback can generally take three forms. The first one is the verbal guidance, in which the teacher tell the movement verbally to the student, and the student have to listen him. The second one is the visual guidance, in which the teacher do the movement and the students have to see him doing it. And the third one is the IT guidance, where the teacher take the hand of the students and they do the movement together. So the aim of this study is to investigate how the verbal, visual, and haptic modality could be used in an immersive collaborative virtual environment to guide the learners' movement. So for this work, we only focus on two manipulation skills, because two manipulation skills are really important skills in medicine. So to answer this question, we conduct an exploratory study to compare the modality. So in this exploratory study, we compared communication modality in teach movement amplitude during a tool manipulation task using visual, verbal, and haptic guidance. For this, we use hand-mounted display and also an haptic arm for immersion and interaction, but also a simplified virtual environment composed by two planes, one red and one yellow, a little blue sphere, and a tool. So the objective of the experimental task was to move a sphere following a movement description, where the amplitude of the movement was unknown for the participant. The experimental task was composed about two phases. The first one is an instruction phase, in which the experimentator instructs participants the movement amplitude and direction using one modality. And the second one was the manipulation phase, in which the participant replicates the movement as quickly and as accurately as possible. So for this, we have the three modalities. So the first one is the verbal modality, so it's a verbal condition, in which the experimenter gives the instruction verbally to the participant. The second one is a visual condition, in which the participants have to watch the animation of the hand of the experimentator doing the movement. And the third one was the haptic condition, in which the participant has to passively following the hand guidance using an haptic arm. So for this experiment, there was 21 participants. It's a within subject design. There is 3 conditions with a counterbalance order, 12 trials per condition. The movement was on the X, Y, Z axis, so 4 trials per axis. And there were 12 different amplitudes that was picked randomly. So for the measure, we measure the movement accuracy with the distance error. We also measure the movement speed with the compilation time. And we also used a subjective measurement, like quality of collaboration between the experimenter and the participant. The modality comparison questionnaire, in which the participants have to choose the modalities they prefer according to some criteria. And the third one is the NASA TLX for measure the mental workload. So to summarize the experimental procedure following this protocol, so in which the participants have to realize 12 trials, and after answer to the NASA TLX and the quality of collaboration, they have to do this 3 times for the 3 conditions. And at the end, they have also to answer the modality comparison questionnaire. So for the result, for the distance estimation error, the mean distance estimation error was lower for the visual condition than for the verbal and haptic condition. The mean completion time was lower for the haptic condition than for the visual and the verbal condition. For the quality of collaboration between the experimenter and the participant felt more close face-to-face with the experimenter with the verbally condition. They also felt that the experimenter was warmer and more friendly with them with the verbal condition. They also felt that the instructor was more helpful with them with the verbal condition. And they also felt a better connection and a better understanding of the instruction with the verbal condition. So for the comparison questionnaire in which the participants have to choose the modalities they most prefer, the results show that visual and haptic was the most accurate to describe the movement, but the haptic was the most disturbing modality for them. It was easiest to memorize the instruction with the verbal condition. And for the visual and the haptic, it was the most educational approach, the most engaging and the most efficient for learning. So to summarize, there are no real difference between visual and haptic, but the verbal condition was the less preferred condition. So we used the NASA-TLX to measure the learner's mental workload according to the modality being used to receive instruction. However, the results show no significant difference between the three conditions with the similar scores among the three conditions. So to summarize, participants were more accurate with the visual modality. They were faster with the haptic modality, and they felt a higher sense of co-presence with the verbal modality, even if the verbal modality was not really the condition preferred by the participants. There is also no significant difference between for the mental workload, indicating that no modality increased the mental workload as compared to these others. As conclusion, we have seen that each modality has its own strength and own weakness. That's why in the future, it will be good to see if multimodal interaction could be the most appropriate approach to improve teacher-learner communication in immersive simulators. So for our future work, we plan to combine modality to study if multimodal guidance is more efficient than unimodal guidance. We plan to explore more complex movements. We also want to study the impact of the modality on the long-term learning outcomes. And we also want to study the impact of this technology on teachers. So answering this question will help us to design a better user interface supporting the transfer of technical skills between a teacher and a learner in a collaborative virtual environment. So thank you for your attention.
Thank you very much, Cassandre. We have time for one or two questions. Maybe I invite also the next speaker to come and start plugging his laptop for the next presentation, please. No question from the audience? Okay, well, thank you very much, Cassandre, then. Okay, so the next talk is entitled Cast Shadow Removal for Cooperative Adaptive Appearance Manipulation. It's a work from the Wakayama University in Japan. And it's presented by Shoko Uesaka.
I'm Shoko Uesaka from Wakayama University. I'll be talking about cast shadow removal for cooperative adaptive appearance manipulation. In recent years, spatial augmented reality is applied in various events as a projection mapping. Unlike projection mapping, the spatial augmented reality enables appearance manipulation with a projector camera system in a dynamic matter. As you can see, the image projection by the projection camera feedback allows us the successive visible appearance manipulation of the printed materials placed on the disk. As an application of appearance manipulation, multiple coaxial projector camera units with mirror reflection enable appearance manipulation of the whole around 3D object. As you can see, the apparent color of the 3D object is changed, not only on the front side, but also on the appearance viewing from the left side of the object. However, in appearance manipulation of the whole around the 3D object, it creates cast shadow like unevenness of projected illumination as shown on region A. This is because the projection from the other unit creates over-illumination, and it will be a disturbance in the reflectance estimation for each projector camera feedback. A pre-measurement of overlapping may solve this problem. However, it restricts application only to the statical scene. To solve this problem, we propose a method of luminance compensation that does not require any pre-measurement or information sharing during projection by the feedback systems in the distribution manner. Before the detail of the proposed method, we first show the result of illumination unevenness removal by the proposed method. In this movie, we place the dwarf figure as the manipulation target between two units and continuously moved it manually, and we applied color phase shift for appearance manipulation for both units. The movie shown on the left is the result of the manipulation without over-illumination correction proposed by Amano in ICAT-EGVE2014, and the right side is the result of our proposed method. Just shadow cast on the nodes was correctly manipulated because no disturbance from the other unit appeared, but excess projections around it appears as cast shadow like illumination unevenness. In contrast, the proposed methods suppressed excess projections and shadow cast on the face by adaptive processing. Next, let me explain proposed control method for dynamic compensation. Appearance manipulation with projector camera feedback use model predictive control based on reflectance estimation. In the manipulation, without over-illumination correction proposed by Amano, the reflectance estimated assuming no overlapping projection, and the appearance manipulation assuming no overlapping projection using reflection estimation. However, it cannot be controlled correctly in the overlapping part. Therefore, at first, we estimation reflectance assuming non-overlapping projection. Next, we determine whether the projection illumination is overlapping area or non-overlapping area. Then, each non-overlapping area, we appearance manipulation assuming non-overlapping projection, and in overlapping area, we appearance manipulation assuming overlapping projection. In the next slide, I will explain about adaptive overlap estimation. In the first step, we calculate reflectance assuming non-overlapping projection. Next, we estimate the overlap from average reflectance trace for threshold determined experimentally. Then, we choose either reflectance estimation assuming non-overlapping projection or compensated reflection estimation assuming overlapping projection from the estimated overlapping state. Then, we performed adaptive appearance manipulation based on chosen reflection estimation. In overlapping area, we appearance manipulation assuming overlapping projection. In the next slide, I will explain how to estimate the reflection. When we estimate the reflection assuming overlapping projection, the problem is the unknown projector from the other unit. The manipulation without over-illumination correction proposed by Amano, projections P1 and P2 converge to the same brightness for phi1 equal phi2. And the illumination contribution should be proportional to the incident angle by Lambert's cosine law. From there, we define degree of contribution. By using the degree of contribution, we estimate the projection from the other unit under the assumption. Then we obtain compensated reflection estimation assuming overlapping projection. Next, let me explain the evaluation environment. Two coaxial projector camera units were placed in front of a 3D target, forming an angle of 120 degrees. The experiment was conducted in an indoor lighting environment with a ceiling light. As each unit worked independently in the distribution system, they performed without sharing captured or projected images. When both units projected white illumination, projection unevenness was caused by the cast shadow. We also evaluated the appearance manipulation results obtained from the proposed method and the method without over-illumination correction proposed by Amano. The result shows the proposed method reduced the projection illumination unevenness by suppressing illumination in the overlapping area. We show the illumination profiles of appearance manipulation along segment A' for both methods. The yellow arrows show the overlapping area, and the black arrows show the non-overlapping area. The method without over-illumination correction proposed by Amano has an average error of 17% due to over-illumination. In contrast, the over-illumination are suppressed and the error is reduced to 4% by using the proposed method. We evaluated results, detected the overlapping regions for each unit. The left shows the ground truth of the number of overlapping projections, and the right shows the estimated projection overlapping. The white and block denotes having the overlapping or not. As you can see, the overlap is correctly estimated on the side surface of the target. However, despite the use of our method, the top surface is incorrectly estimated due to small incident angle. This is because such angle reduces the apparent reflection below the predetermined threshold. This is a limitation of our adaptive overlap estimation. We evaluated the appearance manipulation quality of the proposed method and the method by Amano on various surface colors. The proposed method reduced projection illumination and evenness by cast shadow for most colored surface. However, when comparing A and B or C and D, the compensation error differed according to the color of the reflective surface. In addition, even for same surface color, the error differed depending on the type of operation. It is possibly owing to a different characteristics of the projection. The summary is as follows. In future research, we improve the accuracy and resolution of our method. This concludes my presentation. Thank you for your attention.
Thank you very much. So we have time for some questions from the audience. I'll check on the Discord. We can have a very short question. You mentioned that your method doesn't work well for the top surface reflectance estimation. Do you have any idea on how you could improve that aspect?
Please. Again, please.
You say your method doesn't work very well to estimate the reflectance of the top of the boxes here, the top surface. And do you have, I don't know, maybe not, but do you have any idea on how you could compute a better estimation of this top surface reflectance?
Top surface is incorrectly estimated due to a small indicator angle.
Yeah.
This is elimination and limitation of our adaptive overlapping estimation.
Okay. Okay. Thank you very much. Thank you very much.
Thank you.
Maybe I can call the next speaker. Okay, so the next talk is presented by Theophilus Theo from the Makis group, the Interactive Media Lab here at Keio University. And it's entitled Evaluating Techniques to Share End Gesture for Remote Collaboration Using Top-Down Projection in a Virtual Environment. Theo.
So first of all, thank you, Professor Jean-Marie Labat, for the quick introductions. So today, we are going to talk about our paper evaluating techniques for the remote collaborations, basically using the sharing hand gesture different techniques on virtual reality. So first of all, what is remote collaborations for those who doesn't know, or especially collaborations? Technically, from this picture, you might kind of give you some impressions that it consists of two or at least two or more people to collaborate together to solve a task together. And that means if we put them into different places, then that is remote collaborations. And usually we will denote them as a local user and a remote user, which most of the time, remote user are the one who will provide the support from the offsite, and the local user have the physical task where we will receive the update and also the assistance from the remote user, or maybe they could be in equal engagements. And for those you might already know or can be obviously seen, there are two main challenges in the remote collaborations. The first is, most of the time, the local user might not be able to know the nonverbal communications from the remote user. In most of the case, when a remote user tries to point at certain things, then the local user might not even know what does that mean. And the second challenges will be, how does the remote user know the environments of the local user when they try to describe some things, or when they try to say, are you referring to the one in front of me or even outside of me? So if we try to make it into the bigger picture, we can see that the first is the sharing of the environments and also the sharing of the nonverbal communications, or more specifically for the scope of this paper, sharing hand gestures. So there are a lot of the work has been proposed in the past for sharing environments, but we are going to go a little bit more in the smaller pictures, but toward to the top-down environments. And as the pictures has been shown, you can see that it has a lot of the complicated setup in the past, and even for now, because of the limitations by the technologies, and also, even though that we have a little bit of the enhancements and the advancements of the mixed reality technologies in the recent days, but we are still far from that. So the second limitations in here would be the tabletop setup, or I would say the limited scale, in a way that most of the time when we could put out sharing environments in the remote collaborations, we are definitely limited by the scale of it. And if we want to put it something into large, bigger, like the holoportations or something that can cover the room scale, then the cost can rise up dramatically. On the other hand, sharing hand gestures for the remote collaborations, or as I say, try to share by allowing the remote user to be able to use the hand gestures to show something or to indicate something for the local user, then it could be one of the common techniques that allows the local user to quickly understand what the user are trying to talk about, especially from the remote user. And there are two modes that has been defined so far, which is the local user dependent and also independent mode. The user dependent means that most of the time the hand gestures shared by the remote user will be attached to the local user, and that means that the local user will be able to see most of the time for the hand gesture that has been shared. But in the another side, for the independent, that means that the remote user will be able to walk around as if the hands are actually part of the environments in another way, which means that it gives them the impressions that the local user and the remote user are trying to collaborate as if they are sitting or standing next to each other. And not only that, we also have one of the biggest gap that we want to look at in the scope of this paper, which is try to compare about whether if there's any effect in terms of the user performance, their behavior, or even their preferences when we come across into trying to ask about which method or which modes would be the most suitable for which, or in our case, the object interaction remote collaboration. So because of this, we created a prototype which is based on the social VR platform, VRChat, which is a little bit similar to the cluster, but we are trying to use that to allow us to provide as a simple environments for us to be able to share the verbal and the non-verbal communication. Likewise, we also go a little bit to explore about the sharing environments. So we did down into using the top-down camera, which as you can see from this part of the camera, we have a little bit of the camera that kind of generates the real-life captures and then share it to the local remote user through the 2D projection. But we will go deep a little bit more later. So if you don't understand until now, that's fine. But I would say this slide is the most important for our topic, which is the three modes of the sharing hand gestures. First thing, we have the attached logo, which means that if you look at the top, this is the remote user. And in the bottom row, we have the local user. And the remote collaboration means that the remote user on the top will try to collaborate with the local user to work on the task or to solve the task. So going back to our topic again, attached local modes allows the remote user to be able to share the hands, which in the pictures you can see from the purple, or I would say the blue arms extending outwards from the pictures. And that represents the remote user's hands that has been shared in the environments. So attached local allows the remote user to be able to share the hand gestures by attaching them to the local. Likewise, the attached object means that it allows the remote user to share the hands by attaching them to the task objects. Finally, we have the independent, which means that the places or the positions of the hands will be always following the remote user's positions as if he actually partially coexists in the environments of the local user. So we conducted a quick user study to test about whether there's any effect or can different type of the hand dependency can influence the user, especially on the object manipulation task, and more specific, remote expert collaborations. So we recruited 18 participants and have all of them participated as a remote user role, and us, which is the research investigator, will be playing as the local user or the actor role. And we are going to assess, or we evaluated the assessments in terms of the objective performance and the subjective feedback. And this is the environment, just to quickly run down the tasks. So we have different cubes, and to introduce a task, all of the cube seen by the local user will be in the white color, but the remote user will be able to see the true color of the cubes. And the task goal is, if you look at the square box, which represents of the bigger independent color, that is the goal. And the task is the remote user will be able to use his ability to see the true color of the cube to instruct and to help the local user to put those color of the respective color, those cube of the respective color into the specific zone, or I would call them the task zone. So in terms of the procedure, we start the task from the briefing and following with the training task where we start to quickly run down with each of the different modes for them. And after that, once they are ready, we bring them into the actual task where they go through different amount of the cubes to work on each of the different modes. And that time, we will assess the objective performance, such as the task completion time and the gaze focus. Afterward, once they are done, we go through to the quick questionnaires, where we ask them about the customer embodiment questions, we have the social presence, and finally, the subjective experience, whether if they like or not about the specific method or regarding to these specific sessions. And after they have done that, then we will repeat that entire cycle from the actual task again, following the questionnaire for 2 more times, but for different sessions. And we call the balance that just to make sure that it is not biased to any chance. And just before we finish, we have a post-experiment questionnaire where we ask them for their preference of the choice and some general comments and the feedback. So in terms of the objective performance, we did have a little bit of the measurements and the timing when we try to track the time, which means that as soon as we send the participants to the room where they can start the task, this is the time where we start tracking for the time. And as soon as they finish putting up the last correct cube into the last correct task zone, then that's the time where we stop the task or the task timer. So as you can see from the chart here, the independent hand has a significantly lesser task completion time compared to the attached local, which has the most completion, which took the longest time. And we have the attached object in between each others. For the gaze behaviors, we did a little bit of the investigations to look at if they change their focus or if there are something that might be interested them when they're doing the task. And we can see that the cube attachments can actually depend on how they use, and also the hand dependency can influence how users put their attentions, especially onto their collaborative partners. For subjective performance, don't be overwhelmed by the big bunch of the questions here, but in general speaking, we designed a quick 10, I would say probably 10 or 12 custom questions to ask about the embodiments, which comprise of their agency and their body ownership. And likewise, we did ask a little bit about their experience and the difficulty of doing the task itself and whether they feel collaborative with their partner. Generally speaking, in terms of the sense of the agency, for the independent hand, which has the highest degree of freedom of the movement, give them the highest for the virtual arms sense of the agency. But this is not the case for the attached local and the attached object, but we didn't find any significant result if we compare both of that. In terms of the task difficulty, we did also find that participants slightly say that the attached local is significantly harder compared to the attached object and the independent hand. So we also asked about how they like or did they prefer any specific methods or the sessions. And obviously, as you can see, more than half of the participants significantly prefer the independent hand, and more than 80% of them say that the attached local is somewhat unpleasant to them. We did collect a little bit about the comments, but because of the time, I will just quickly run down that. So starting from the attached local, most of the participants say that they doesn't really like it because they have to focus their partner, and sometimes or most of the time, the communication is confusing to them because they have to adjust the arms accordingly, and it is just not efficient. Going to the attached local, we have some comments about it is really fun because it is a new method that has been used by them. They didn't really explore about how they can see the arms coming from the cubes. And yeah, they feel that it is easier to point, although they couldn't really move in these sessions. Finally, we have the independent hand, which we have a lot of positive feedback about that. Like they say that the communication is really fast and it is really clear they can understand their partner, which it seems that it is also possible for them to do the task without any verbal communication. So to quickly discuss that, the embodiment experience and also the problem-solving strategy definitely influenced by the hand dependency in the remote collaborations, specifically how the participants will be able to change their task behavior, such as for the independent hand, we will have the remote user standing somewhere between the task cube and the task goal and try to put the hands onto the cube at one place and the another hand pointing at the goal to kind of give a quick indications about where to put and where to pick. But for the attached logo, they don't really have to do the first pointing part. They just have to pick the cube, and then they repeat the similar action for the independent hand. But for the attached logo, they have to do a little bit of the frustrations because of the 2D projections that couldn't really give them the depth perception, so they have to really keep telling the user which one are they really referring to. So the takeaway from here, we propose a top-down immersive remote collaboration prototype to explore about whether there's any whether there are any effect in terms of hand dependency in the remote collaborations, which we found yes, it definitely has something that can change the user gaze focus, the user behavior, and finally the sense of the embodiment on the virtual hands. So which we think that this might be important because this will help them to be able to decide, especially for the future works, to know which technique might be optimal for which collaborations or which paradigms, such as for the telepresence, remote work, and active monitoring. Thank you for staying with me until now, and I will start accepting any questions.
Thank you very much, Theophilus.
Thank you.
Are there any questions? Yes.
Hello. Could you explain a bit how is this compared to, let's say, if both avatars of two users were on the same scene? Thank you.
Thank you for the questions. So the reason why we are trying to explore this is because based on how latency, or probably I would say when we talk about remote collaborations, something that we have to think about is the latency when we try to share the bandwidth. And if we have more information that we try to consider or try to put into the remote collaborations systems, then they can kind of cause a higher up, or I would say the larger latency, or reduce that in another way each other's. So because of this, we are thinking about if there's any way that can be significantly easier for us to be able to explore that. But in terms of the avatar, we did use the inverse kinematics to handle the algorithms for the rest of the body gestures and the movements.
Thank you. Is there another question? Maybe I can ask one just to make sure. On the attached object metaphor, how did you choose which cube was going to have the arms attached to it?
Yes, thank you for the questions, and sorry for not explaining that clearly. So for the object attachments, or I would say the attached object conditions, the remote user have to actually pick the cube, which is actually overlaid on the floor by themselves. So if we go back to the slides in here.
Okay, so it's the remote user that selects it. Huh?
Yeah, okay. So that means that the remote user will have to actually be able to see the hitbox, or I would say the collision box, where they would just use their hand or probably the hand controller to point at the cubes, which allowed them to be able to put their hands into the corresponding area.
Okay, so that means you have only one object at a time that you can interact with.
That's right.
Did you think about what would happen if you have, I don't know, multiple objects to be interacted with at the same time?
For the scope of this paper, no. But for what personally I would say, that would be really interesting to explore how it might cause the multi-embodiments, and also how that, such as the user attentions and also their several focus, might take into consideration, especially in the remote collaboration. And also the group collaborations consists of 2 or more people.
Yeah. Okay, thank you very much.
Thank you.
Is there another question? Okay, thank you then. Thank you again, Theophilus.
Thank you very much.
And could you please, the next speaker coming to set up the computer? Okay, so the next paper is called the Data Collection Protocol Tool and Analysis for the Mapping of Speech Volume to Avatar Facial Animation. And it's a work from the Nara Institute of Science and Technology. Presented by Ryosuke. Probably you just go. You can do this, you can shake, and then you have to go there. Should be right.
So let's start. Hello everyone, I'm Ryosuke Miyawaki from cybernetics. Oh. Sorry. Some trouble. Oh. Yeah. And I hope it works. It looks a bit. It looks good, thank you. Okay, so let's begin. Okay, again, hello everyone. I'm Ryosuke Miyawaki from the Cybernetics and Reality Engineering Lab, Nara Institute of Science and Technology. Today, I'm going to introduce our research, data collection protocol tool and analysis for the mapping of speech volume to avatar facial animation. And avatar animation is traditionally done with motion tracking system. However, this method is expensive and mostly used in movies. Therefore, data-driven method to animate avatars have been proposed. These days, communication using avatar is increasing. Due to the pandemic, communicating online with the others has become common. In that sense, avatar-mediated communication has a big potential. For example, we can communicate with our own avatar by using a tool called Mesh for Microsoft Teams. Not only video chat tools, but also avatar creation tools are becoming higher quality, easier to use, and more familiar. A good example is a MetaHuman Creator, where the people can edit high-fidelity avatars. As avatar creation is becoming accessible, the understanding of human behavior for how to animate an avatar is also increasing. A possible way to get insight into the animation of avatar is to use multimodal dataset. LSR3 is a large audiovisual dataset for lip reading. It is not tailored to create avatars, but it is a good example to use an existing dataset for the understanding speech-related visual processes. There are previous work to define animation model for speech called JALI. And they use this model to express avatar animation, giving audio and speech transcripts as input. To define its movement, they use facial descriptors. These descriptors are derived from the facial action coding system, or FACS, and are called action units. And in this example, the researcher used the FACS to discuss human facial behavior as a common interpreter. However, even though it is easy to precisely communicate a particular facial movement using the FACS, estimating action units is computationally expensive, and it is still a difficult task to do with current software. To overcome limitation of the FACS, a brain shape-based facial tracking system can be used. Branch shapes is an interpolation method to animate an avatar. Here, we can use this and facial descriptors using relative displacements from a neutral face. There are varied types of branch shapes, but the ARKit branch shapes made an effort to standardize them. In here, I'm showing mouth funnel, nose near left, and jaw open, and brow down left. And there are 52 types of facial branch shapes defined in the system, and they are widely used. In fact, Rocketbox Avatar Library and MetaHuman are compatible with these branch shapes. Branch shapes can be used directly as an alternative to FACS. By directly mapping branch shape tracking values into avatars, we reduced accumulated errors derived from action unit detection and mapping back to avatar branch shape. Therefore, we propose a protocol to an analysis of an avatar animation. And our objective is to support multimodal data, especially for avatar animation. To achieve this, we propose a data collection protocol and an open source tool. By using our system, we also analyzed facial movement and tried to find importance movement on facial animation. We hope that this enables other researchers to collect data for analyzing human facial behavior for avatar animation. We considered 3 modalities: facial video, speech audio, and facial movement. For the facial movement, we used a branch shape-based facial tracking. And here is an overview of the proposed web-based recording system and its setting. The user can record both audio and facial video and simultaneously record facial movement with an external app compatible with ARKit branch shapes. The web system allows users to proceed with the recording while viewing their own volume levels and scripts to be read. The volume indicator looks like this, the green bar. The same timestamps are used to synchronize the data, the both data. With this, it is possible to collect standardized multimodal data. The branch shape tracking is done with a live link face. This is a free app developed by Epic Games that can collect 52 branch shapes and 9 rotations with 60 FPS. The tracking values are normalized as shown in the image. The tracking range goes from 0 to 1 for branch shapes and -1 to 1 for rotations. And these time series values are given per branch shapes, and we can use them directly to analyze facial movement during speech. Here, we practically used our system to collect data and perform simple analysis. In the experiment, 9 participants kindly helped us to examine facial movement when speaking the same script at different volume levels. We used Japanese script called Ita Corpus, developed by Japanese Phonician. By asking participants to read the scripts, we can collect phonemically balanced data. Also, we set 4 conditions to generate 4 volume levels: muffled, low, normal, and high. The participants were asked to speak at these perceptual volume levels by using our system. And while the participants were doing the task, we recorded speech audio, branch shapes, and head-eye rotations, and facial video. And this is the setting of our experiment. And as you can see, we only require a lighting set, a display, a microphone, an iPad, and a RGB camera. And this is the procedure of the experiment. First, the participants were given explanation, and then they signed the consent form if they agreed to participate. And as a preparation, we clipped their hair and calibrated their position, face, and speech volume. For the recording phase, they read 100 scripts and pronounced 5 vowels for each condition. And each condition took 15 minutes, about 15 minutes, yeah. And after recording, they indicated if they would allow to disclose their data in a separate consent form. And this is an example of facial video recorded by our system. And along with facial video, I also put an animated avatar created by MetaHuman with its movement. The script was 嘘でしょ? It looks like this.
嘘でしょ?
It's a normal condition.
嘘でしょ?
It is the lowest condition.
嘘でしょ?
Low condition and
嘘でしょ?
The high condition. So I hope you can find the differences. And we conducted simple analysis for facial movement. We used 61 types of facial movement in the 4 conditions. We set a question, which movement changed between conditions? So to check this, we investigated if the facial movement changed significantly during speech at different volumes. And here, this is the pipeline of processing facial movement. We extracted data within time of reading script and remove irrelevant movement using result of voice activity detection. And for the third step, I removed 2 short frames with script as a validation. After that, I averaged facial movement values per script, per condition as a main processing, and then finally, we performed statistical test. This is the result of the stats test. And finally, we extracted 15 out of 61 facial movement recorded with external app were significantly different at least 1 pair. Of course, around jaw and mouth movement were significantly different. But surprisingly, we've also found around cheek, like this movement, nose movement, and head pitch as well. So this result indicates the importance of not only jaw or mouth, but also cheek and nose in speech animation. And here are the primary contributions. First, we released an open source web system for recording facial video, speech audio, and facial movement with a script and audio indicator. The facial movement were recorded with an external app. Second, we opened OSF repository to check our reproducibility. And you can get our dataset after the submission of the agreement form. Yes, so and you can access both 2 links in our paper, so please check. And third, we showed a simple analysis of facial movement. Our findings indicate the importance of speaking animation not only around the jaw and mouth movement, but also nose, cheek, and head pitch. Okay, that's all of my presentation. Thank you.
Thank you, Yosuke. Do we have any questions? Yes, thank you.
Okay. Do you believe that changing the language would change these results? This is my first question. And the second one is, do you believe that the data collected could be used in a deep learning technique, let's say to generate, auto-generate in the future, all the facial animation that we need? Because I think this is the end game. Thank you.
Okay. Thank you for your question. And in general, Japanese has less phoneme compared with English. So, which means, yes, the first question, yes. So I think we could find a difference among the language. And the second question, why I do this research is to use this collected data for the machine learning. Yeah, so yes, so you pointed out is what I aimed. Thank you for your question.
Thank you. Any other question? Nope. Okay, thank you very much, Yosuke.
Thank you very much.
Okay, and then this is our final paper for the first session. It's entitled AR Object Layout Method Using Miniature Room Generated from Depth Data from the University of Tsukuba, and I think it's Keiichi who is going to present it.
Hi, I'm Keiichi Hara, and I'm a master's student in University of Tsukuba. Today, I'd like to talk about AR Object Layout Method using miniature room generated from depth data. In AR, users can place virtual objects on real environment and arrange them depending on their purpose. Here, the user is moving virtual objects near his desk, and then he's moving another object, scaling it, and placing it. AR users can lay out objects like this. However, existing AR layout methods are time-consuming and physically demanding. To support users to create AR layout, we aim to create a system that reduces physical workload and shorten manipulation time. Next, I'll explain a related work on virtual object manipulation in AR. We can divide object placement techniques in AR into two categories, manual and automatic. First, we will explain the manual placement technique. A common technique in AR is hand ray manipulation, and as shown in the previous video, virtual ray emitted from the hand is used for selection, movement, and scaling. The next method uses edges and surfaces, and objects can be placed along edges or surfaces. And the next method uses room deformation, which virtually compresses the room to the front and move all objects to the front. On the other hand, in automatic placement, there is a method that uses the meaning of the real objects, or the method that uses the shape of the room. In this study, we focus on the manual placement technique. I will describe the features of the manual placement technique. We evaluate them in 4 categories: manipulation time, physical workload, ability to place freely in a 3D space, and ability to check layout immediately. The disadvantage of hand array is that the physical workload is high. The disadvantage of using edges and surfaces is that users cannot place virtual objects freely in a 3D space. The disadvantage of using room deformation is that users cannot check the layout immediately. Therefore, in this study, we aim to develop a system that is useful for all of the 4 categories. Next, we will explain our work. In our approach, we use the world in miniature technique in AR to support the AR layout. The world in miniature technique is one of the virtual object manipulation techniques in VR, and by using the world in miniature technique, users can manipulate virtual objects by manipulating miniature objects in the miniature room. In our system, we use depth sensors attached to an AR device to acquire a 3D mesh of the room. We then scale the mesh down and display it in front of the user. We call it the miniature room. In addition, we display a miniature of the virtual objects in the miniature room, and we call it the miniature objects. In our previous work, we created a prototype and conducted a preliminary experiment. In our prototype, we created the miniature room in a simplified manner using a wireframe mesh. In our preliminary experiment, we did not use the miniature room, but only evaluated the features of the manipulation of miniature objects. Therefore, we used a simple manipulation task, only using spheres, and the target positions were predetermined. In the preliminary experiment, we found that scaling manipulation was difficult using miniature objects, so we added functions to support scaling manipulation. Then we evaluated our system with a task that is similar to the actual layout situation. To do so, in our task, we used various objects and asked participants to create AR layout by their free will. Next, we will explain about our system. In our system, we use a miniature room with surfaces on a wireframe. The mesh of the miniature room updates in real time within the range of the depth sensors. Users can move virtual objects by moving miniature objects like this. And additionally, users can scale the size of the virtual objects by scaling the miniature objects. Here I will explain the system configuration. Our system uses depth sensors attached to HoloLens 2 to acquire the depth data of the user's hands and the room. Our system then uses the mixed reality toolkit to recognize our hand movement and create a 3D mesh of the room. The resulting mesh is then scaled in our Unity application to create a miniature. To support scaling manipulation, we added 2 functions. First, in our system, the size of the miniature can be changed by switching the manipulation mode in the hand menu. Therefore, users can make the miniature large if they feel that it is difficult to manipulate miniature objects. Second, we added a bounding box to the miniature objects so that users could manipulate small miniature objects. Next, I will explain about our evaluation. In our experiment, we evaluate the physical workload and manipulation time of our system in AR layout. To conduct a task that is close to the actual AR layout situation, we used various objects, including 3D objects, 3D icons, and 2D windows, and asked the participants to create an AR layout by their free will. In our experiment, we used a room with 2 desks, and we asked participants to select objects from a hand menu. And by selecting an object, the object displays in front of the user. We conducted the experiment in 2 conditions. This is the miniature condition, which uses our system. In the miniature condition, participants could only use the miniature manipulation explained before. Then this is a hand ray condition. In the hand ray condition, participants can only use hand ray manipulation. We did not show the miniature in the hand ray condition. We asked participants to lay out 16 virtual objects around the room, around the desks, and this is an example. We conducted the evaluation with 12 participants within subject design. For measurement, we obtained the manipulation time and conducted workload questionnaire, NASA TLX, and open-ended questionnaire. Next, I'll explain the results of the evaluation. First, I'll explain the results of the workload. As can be seen in the graph, the workload was significantly smaller for our system in physical workload and time pressure. In the open-ended questionnaire, we obtained comments about physical workload. They mentioned that by using our system, they could manipulate objects where the arms would not get tired and manipulate with small movements of their hand. These factors might have affected the physical workload. Next are the results of manipulation time. No significant difference were found in total manipulation time. However, after dividing the manipulation into moving, scaling, and confirmation of placement, our system was significantly longer in confirmation of placement time than miniature condition. In the open-ended questionnaire, we obtained comments about confirmation of placement. This comment suggested that the manipulation in our system could not be completed only by looking at the miniature, and it was necessary to look alternately at the miniature and the real environment. And this could be one factor that our system took a longer time to confirm the placement. Last, I'll explain about limitation and future work. In this experiment, we asked the participants to use only miniature manipulation in miniature condition, although it is possible to combine hand ray and miniature manipulation. Additionally, we could improve the UIs in the hand menu. This is all for my presentation. Thank you for listening.
Thank you very much, Keiichi. Are there some questions?
Sorry for doing all the questions. So, if I understand correctly, the tests were done with the same number of objects in the same room, right? If I understand correctly, the tests were performed with the same number of objects in the same room, right?
Yeah, 2 conditions. Yeah.
Have you considered what would happen if we changed the complexity of the room, let's say an empty room versus a room with too many surfaces like this room? And what would happen if, let's say, instead of 12, we had, let's say, 100 or 50, or we could emulate, let's say, a movement, or we could grab the miniature more than one object at a time? Thank you.
First, thank you for your question. And first, we used only one room, and in the open-ended questionnaire, some participants said that the room size might affect, and if the room get more larger, it might reduce the manipulation time in by using miniature, because if using handwave, people need to move to the objects to near to the objects. But by using miniature, whether the room is large or small, users can move it without moving.
Thank you. Any other question? Okay. Wait.
Thank you for the presentations. So I assume that the participants will be able to scale the objects of the existing objects. Is that right?
What object did you say?
So in the task objects of the existing objects, when participants try to manipulate them, can they change the size of the objects?
Yes.
So did you notice any, or did you find any significant friend or any effect in between the conditions, the hand ray and the miniature? Because I will assume that the miniature will discourage them to scale them into much more smaller size because of being harder to manipulate. But in the hand ray, where micro gestures or micro manipulations can be easier. So did you find any effect or any result where participants, for example, make the objects much smaller generally in the hand ray, but not, or maybe bigger in the miniature?
As we added functions to support scaling small miniature objects, like adding bounding box or making available to scale the whole size of the miniature. The result of the manipulation time, there was no significant difference, but the scaling time was a little bit lower than a hand ray condition.
Thank you. Another question? Okay, then thank you again, Keiichi.
Thank you.
Everybody was very respectful of the timing, so we are a bit early, but that's okay, I guess. That will leave us a bit more time to grab a coffee or something. We'll see each other, I think, in 28 minutes. We come back here to start for the next session. Thank you.
All right, so I think it's time to start the session 2 on haptics and remote. My name is Kyoshi Kyoka from Narrow Science Technology. I'm happy to be chairing this session. So we have very good 4 papers. So the first talk is progressive tiling and cutting of soft bodies in high-performance virtual reality. And this is by the Greece people, and then it's going to be presented by Manos Kamarianakis. Please.
So, Hello all and welcome to this presentation. My name is Manos Kamargiannakis and today I will present you this work titled Progressive Tearing and Cutting of Soft Bodies in High-Performance Virtual Reality. This is a joint work by various authors affiliated with University of Crete, University of Western Macedonia, the Foundation for Research and Technology Hellas and its spin-off startup company Orama VR. So, a brief overview of my presentation is the following. I will present you the team and the problem that motivated us, and then I will present you our approach and specifically the TR algorithm. Finally, I will conclude the work and hopefully, if time permits, I will give a live demo of 1 or 2 minutes. So, the team behind this work is myself, Manos Kamargiannakis, Dr. Adonis Protopsaltis, Professor George Papagiannakis, and our 2 developers, Dimitris Angelis and Michael Tamiolakis. We're all Greek people. As builders of the medical training metaverse, we are motivated of the metaverse and how to provide tools to create it. Here you see a short video from Meta that shows a surgeon in virtual reality performing a tear in a heart, a surgical tear. This is now a concept, but we want to make this a reality. So what does it take to be done? What are the action items? So we want to replicate high-fidelity surgical operations in virtual reality. And in order to do so, we definitely have to be able to perform real-time surgical tears and cuts, even in untethered HMDs that have lower CPU and GPU specs. We should be able to perform them anywhere on the model, not just in predefined positions that the current state-of-the-art is. In order to do so, we have to use simple geometric algorithms that yield satisfying visual results, and that this solution should be able to be applied to any 3D surficial model that are vastly available in the market. Finally, we're focusing on realism, so we want the user that in virtual reality makes movements similar to a surgeon to obtain a result similar to a surgeon would see in the actual operating room. Our approach consists of 3 components: the TR algorithm, the CAT algorithm, and the soft body framework. All these are already implemented in Unity 3D, a modern game engine, and our freemium platform, Mages, developed by Orama VR. Due to time limitations, I will talk mainly about the TR algorithm, and let's see what we have achieved so far. On the left is the video from the Meta you see here, and next is our result. This is in real time using a tethered HMD. You see a heart. Actually, this is a surfacial model of a heart. It's pumping, but actually this is done by the soft bodies framework. And we have freely cut an artery, and we can then, you see, we can move the torn arteries, and it's really realistic. So, how have we done this? This is done mainly by the TR algorithm and the soft body synergy. The input of this algorithm is a 3D surfacial soft body model and the scalpel's position of the user. So we sample, as the user moves the controller, we sample the scalpel. And finally, we want to obtain a torn model that is properly soft-bodied in the sense that I will explain later. The TR algorithm is, can be broken down to this flowchart. And if you properly see, you will see that mainly simple tests are required. Simple geometric tests, sideness tests, and interpolation primitives. But let me just put it simply in images. So on the top left, you see the bunny and the scalpel positions, and between 2 consecutive scalpel positions, we define a bounding box of, defined by 6 planes. Okay, so if we identify the intersection of this bounding box and the model and remove this intersection part, it's like we're having a single tier. If we do it for all 2 continuous scalpel positions, then we will end up in the final top right position where the bunny is completely torn. Some things to take care and to speed up things, because each time we do a sideness test, probably we have to go through all the edges of the model and through all 6 planes of each bounding box. So let's say tip 1, we can segment the model to speed things up. And as a second tip, we have to take extra care of where the two consecutive bounding boxes intersect, because due to the overlapping, there will probably be some artifacts, so we need to tamper a bit with the planes defined there. After the tier is complete, in between each tier step, we have to update the particles. So even if you don't know what a particle is something that connects various vertices like a control point, and when you move it, it moves also these vertices. In the initial model, the particle you see here as a sphere is connected to all the vertices of the model shown at the edges of these segments. But after the tier, some vertices lie on opposite side of the particle with respect to the tier, so we have to cut them and no longer be connected. This helps us to recreate a realistic scene you see in the next slide. And to avoid artifacts, we also consider not just the tier that is going on right now, but also the previous one. So if we do update the particle, you will see that we get on the bottom right a more realistic result as compared to if we have not updated the particle, which is the top right. And of course, the particles tend to go back, so if the user interacts with them, let's say it pokes the model, they move them from the resting place, and they always tend to return back like a spring. So in running times, we have achieved, using non-parallel CPU computations, we have achieved running times that are capable of yielding real-time results, as you see in the video, and I will show you now on the demo. And this can be amended in almost most cases to achieve real-time results in untethered HMDs too. So summing up, we have crossed all our action items, and of course, things always remain to be done. So all these things are now running in CPU non-parallel, and using GPU shaders, we could actually really accelerate this process, and we could use an offline finite element method to actually see what would be the ground truth, so how the model should be actually be deformed, and compare it with our to also obtain not only visual results, but qualitatively evaluate how realistic is our visual results. And of course, we would like to future connect with machine and deep learning techniques, let's say, to see what's the best model segmentation, or if a user has stopped performing a tier. So, do I have 1 or 2 minutes? Yes, great. So, great. Great. Okay. Do you all see my screen now? Is it casting? No, it's not. Okay. Are we casting now? Yes. Great. Okay, so what we have here is some fat. Sorry for this. This is a body that we have applied soft body. So let's see. Okay, and now we can have the scalpel. Sorry. Okay. And of course, if I don't mess it, you see it? Oh, it's spreading like it should, and this is done in real time in an untethered Oculus Quest 2. Okay, so thank you very much. That's all from me. Thank you.
Thank you very much for nice talk and demo. Any questions? Comments? Let's check online one. So far, I don't see any question. Okay, so I will start my question. So, yeah, it looks great, and then I'd like to try it myself. But
yes,
at the same time, the deformation could be a bit more real, so that it looks like
yes,
deformed too much and doesn't look like a real organ.
Let me put it back.
I don't know why, but
sorry. Can you switch? Am I doing something here? I'm not seeing. This is not my image. Ah, okay, great. Okay, so.
Can you use the microphone?
Yes. Okay. So. This part here, or let me check. Let me better show you something different, like this one. Okay, so.
It looks more like a balloon or something.
Yes. We can achieve realism by doing the following. Here we have set the particles to follow a natural movement.
Keep holding the microphone.
Okay, sorry. Here, let's say we can show how a heart can look like it's probably pumping by using the particle system, and we move the particles, we set them in a specific sequence, and it replicates. The actual skin, let's say, we want to tear, does not, let's say, it doesn't move by itself. Okay, so you can nudge it, you can poke it, and it has some elasticity, but by itself, it does not move, right? So that's what the fat was trying to replicate. So if we nudge it, it will move. If we don't, it won't. But in some other cases, such as organs, livers, etc., maybe we have to have a natural movement in bowels, etc. So if we want, we can also achieve this. Okay. Thank you.
Okay, thank you very much. Any other question? Because I was also wondering if he can, after the surgery, if he can sew the two separated parts.
This is actually work in progress, yes, and this is the actually, it's part of the future work. It's in a current other project, so feel free to expect another paper in a year or so regarding sewing. But yes, we can do, we can also cut, we have not presented, we can also drill, which is useful for, let's say, for dents or something like that. And yes, we're trying to build the metaverse as much as possible.
Okay, thank you very much.
Thank you.
So, do we have any short question? Okay. Otherwise, let's thank the speaker again.
Thank you. Arigatou gozaimasu. Thank you. I will keep this here.
Right, second talk of this session is titled An Integrated Ducted Fan-Based Multi-Directional Force Feedback with a Head-Mounted Display. And this is by the Keio University, and it is going to be presented by Koki Watanabe-san. Please.
Hello everyone, I'm Koki Watanabe from Keio University. I'd like to talk about integrated ducted fan-based multidirectional force feedback with a head-mounted display. First, force presentation technology is technology that makes you feel as if there is an object or reproduces the reaction force which occurs when an object is touched. The device on the left is the example of grounded type, and the right one is wearable type. In contrast to the grounded type, the wearable type is suitable for mobile applications, but it is difficult to present a strong force. These techniques generate force feedback to the hands, but there are also studies which simulate haptic feedback on the head, because the human head is superior and sensitive to spatial awareness, which affects immersion. The left one is I can simulate motion through force feedback by attaching the grounded robotic arm to the HMD. And the right one has a belt spring system to push the HMD towards your user's face. But these techniques have bottlenecks restricted by the hardware configuration. The left one is allows the user to move within the movable range of the robotic arm, and right one is limited to producing the backward force. So some studies use thrust to solve this problem. The left one uses airjet to produce persistent force, and right one is the helvet-based system that can simulate gravitational force. But no device has been proposed that can present strong force to the head in multiple directions. So our purpose is to develop a portable force feedback device which can generate strong force to the head in multiple directions. In this paper, we introduce a head-borne force presentation prototype which generates strong force in multiple directions by using ducted fans. We attach 4 ducted fans to 4 corners of an HMD, like this figure on the left. And so it can produce 3 DOF force consisting of translational force on the front-back direction and rotational force in the yaw and pitch directions. So ducted fan is a propeller-shaped fan installed in a cylindrical duct. It is often used for the radio-controlled airplane, like this picture on the right. And the duct serves as a barrier to trap and concentrate the window to reduce the aerodynamics loss of the wind force generated by a propeller. To explore the force feedback with the ducted fans, we assess the force characteristic generated by a ducted fan. First, we measured the thrust of a single ducted fan relative to the pulse width of the PWM signal. The result is shown in the figure. The propeller rotates in counterclockwise directions when the pulse is smaller than 1,500 microseconds. And if the pulse width is larger than that value, the propeller rotates in clockwise direction. So we can see that the magnitude of force is proportional to the pulse width, and the maximum force of positive and relative rotation were 5.69 Newton and 2.35 Newton respectively. Next, we measured the noise level of a single ducted fan relative to the pulse width. The result is shown in the figure above. Forward force produces noise up to 92.6 decibel, and reverse force produces noise up to 110.6 decibel. So this suggested that earplugs should be worn to protect the user's hearing. And when adjusted to the sound level below the 90 decibel, which is a safe sound level for human ears, the range of the pulse width is available. And then the magnitude of force that one ducted fan can produce is from minus 0.23 Newton to 1.33 Newton. So next, we measured latency in force presentation. We tracked the changes in force value for 2.6 seconds since the signal was sent by the virtual environment. The result is shown in the graph. So we can see that the prototype had a latency of 500 milliseconds for generating a force and 110 milliseconds for stopping the fan. Next, I'll explain the net force with four ducted fans. If the output of each fan is represented by a letter, as shown in the figure on the left, the net force is as shown in the table above. And maximum net force that the prototype can output and maximum net force within the acceptable limits of the human ears are as follows. And we designed a virtual environment alongside software to communicate between the environment and the hardware. The following figures shows a flow when a collision occurs in the virtual environment. First, the motion capture camera acquires the user's position and updates the position in the virtual environment. And then the Unity sends the force information to the microcomputer, and the PWM signal input from microcomputer to electronic speed controllers are converted into input signal for each fan. Finally, each fan is controlled by a microcomputer and the ESC. Next, we designed a user study to investigate the absolute detection threshold when using our prototype. The procedure is as shown in the table on the left, and there are 10 participants consisting of 8 males and 2 females. And there are 6 directions times 2 equals 12 conditions. And the participants went through the experiment while sitting. And it took 40 minutes on average. So the results of the ADT is as follows. We can reduce power consumption by omitting outputs below these results. Next, we conducted a follow-up study to evaluate the effects of using our prototype in a VR flight simulation that simulates wind pressure and an event of virtual physical impact. The experimental conditions are shown in the table. There are 10 participants, which are the same as in user study 1. And the participants went through the simulation with 2 conditions, with or without the force feedback. And we evaluated the user's immersion, enjoyment, reality, comfort, visual haptic match, and side effects of vibration and noise, and participants' simulator sickness. And it took 1 minute per condition. The results of custom design questions are as follows. We can see that our prototype enhanced the immersion, enjoyment, reality, comfortable, and visual haptic match scores than a standard VR simulation, which are without force feedback. Next, the results of SSQ is as follows. Among the subscales, the force condition performed better than the no force conditions. So this suggested that applying force feedback on the head by using our prototype can reduce simulator sickness. And I'll explain limitation. First, noise and vibration may disturb the experience when the force presentation is presented to the user. And second, the user may feel uncomfortable with the fan placement because of the HMD-centric design. And we are considering adding a vector nozzle to increase the presentable force directions. Our conclusions is as follows. Thank you for your attention.
Thank you very much for the very interesting talk. Any questions?
Thank you for your presentation. I thought that that system looks quite heavy. How long do you think user could use this system? Is it possible to use it like longer than 5 minutes?
It weight 1,300 gram, I think. This is including the HMD.
How long could the user use? How did you evaluate the workload of the user's physical workload?
Yes, in the user study, the user feel uncomfortable with the weights. So, yeah, we need to consider that making the device more light.
Okay, thank you.
Any other questions? Is there any question online? Okay, otherwise, yeah, I have a couple. Actually, I really love your device, particularly about the extreme-like form factor. And I was wondering why you put the dark fans around the head-mount display, not around the center of rotation or center of mass of your head.
the reason for this is it is easier to attach the ducted fan to the HMD. So yeah, in the future we attach the ducted fan for head-centric design.
I see.
Sorry.
Okay, any other questions? How noisy is it?
So loud. Yes, so loud.
Can you enjoy some audio content while you're playing with the X-Wing device?
In the user study?
Can you listen to some audio content?
Yes, a little.
Okay. So I see no questions. Okay, so let's thank the speaker again. All right. So in my understanding, the third and the fourth talks are online. So let's move on to the third one. Third one is entitled Progen VR, Natural Interactions for Procedural Content Generation in VR. And this work is done by the two institutes in Portugal. And I believe that the talk is given by Bruno Carvalho. Daniel. Oh, Daniel Mendes, the second author, is going to give a talk. Okay, so are you ready? Yes, please start.
Just a minute. Okay. Hello, good morning from Portugal. I am Daniel Mendes from the University of Porto, and I am here to present our paper entitled Progen VR, Natural Interactions for Procedural Content Generation in VR. 3D content creation is a complex and time-consuming task, usually carried out on desktop environments in editors like Maya or Blender with WIMP-style interfaces. It is used to create digital content like virtual worlds for television, cinema, and video games, machine models for engineering and the manufacturing industry, and so forth. However, editors based on WIMP and 2D screens have a few limitations. The first is that the input space is limited to the two-dimensional movement allowed by the mouse, making it difficult and awkward to perform certain kinds of 3D operations. And the 2D display output space where the 3D scenes and models are visualized are also limited. And the user's perception of shape, depth, and size would be improved if a stereoscopic visualization was employed instead. To overcome those issues, 3D immersive editors with spatial input have been researched. However, despite the more natural interactions they offer, translating certain tasks from the traditional to spatial inputs is not trivial. A set of tools which have become highly relevant in the creation of large 3D scenes is procedural content generation tools. These tools enable the generation of multiple entities automatically, following a set of rules which can be parameterized. These rules can specify, for example, the scale and position of multiple generated objects, transformations applied to them, and the number of repetitions to, for instance, populate a forest with trees or even create an entire city. To create variations and avoid repetition patterns, randomness is often used. If this poses some challenges to users, in particular to non-technical ones, as many artists are, their usage in an immersive setting is even more daunting. To address this challenge, we propose Progen VR, a novel approach for creating 3D scenes in an immersive environment, using natural interactions and procedural generation techniques. We resort to a set of simple rules that users can apply to existing models and use as building blocks to hierarchically create complex scenes. Our approach considers a model as a composition of various static assets with hierarchical relationships between these and procedural rules to change their visibility status, placement, and orientation. Users have core modeling operations available to build the model, such as cloning and moving objects, entities, such as groups and uniformly spaced tilings, and an assortment of randomization operations and objects. The randomization allows users to clone models, generating a different outcome following the specified rules. This tool can be helpful for quickly spawning several city blocks when creating a city, or generating different rooms at runtime that the player can explore. Our modeling approach starts with loading primitive objects into the scene. We call the initial assets primitive objects because they do not have any procedural rules and can only be moved around and copied. They cannot be edited or partitioned into smaller blocks, unlike procedural objects. Procedural objects can be either composite or randomized. When creating these procedural objects, all types of objects might be used, both primitive as well as other composite and randomized objects. Composite objects are those which contain a set of other objects, such as a group. A group is created by selecting one or more objects and then joining them into an aggregate object. Once formed, the group can be moved and rotated as a single object, and its elements keep their relative distances and orientations. Another composite object is the tiling. A tiling wraps a single object and lays out a fixed number of clones of this tile along a straight line with uniform spacing. The number of tile clones, the spacing between the tiles, and the orientation of the tiles can be adjusted, and the tiling direction can be changed by rotating the tiling object itself. To create grids of objects, a tiling object can be used as the child of another tiling object, as we can see in this example. Randomized objects are objects that can assume different forms or properties, either by selecting a random object from a given set or applying randomized transformations to an object. The first procedural object is the random, which can be constructed in a similar way to the group, but instead of merging all objects, shows exactly one of these chosen randomly. Upon creation of the random, the variants retain their world space orientation, but snap to the position of the first selected at creation time, although this can be changed later. The mover adjusts an object's location by applying an offset chosen at randomly from within a defined three-dimensional offset range. This can be used to create variations of an object that does not appear in the same position. For instance, it can be used within a tiling object to create a row of objects that are not perfectly aligned. The rotator is similar to the mover, focusing instead on object orientation. It adjusts an object's rotation around one of the primary axes by a random angle chosen randomly from within a defined angle range. The last object type of our approach is the empty object, which behaves identically to a primitive object, but it is actually invisible. This object can be used to represent the concept of nothing amongst the variants of a random. The visibility of empty objects can be toggled on and off, so they have a visual representation the user can interact with. Besides moving entities and creating and editing procedural objects, there are other operations available to users. A clone operation can be applied to any object, and it creates another instance of the same object with its children cloned recursively. The object tree of the clone is identical to the original, therefore following the same rules. Cloning a primitive object creates another primitive object with the same asset, and procedural objects are cloned by reference, becoming linked. When an object is modified, the modification automatically propagates to all its linked objects. A reroll operation can be applied to any object, and it requests the object to make a different set of random choices, recursively down the object tree. When applied to a primitive object, it does nothing. When applied to a random object, it requests that another variant be shown and that the shown variant itself be rerolled. When applied to a group or a tiling, the elements are themselves rerolled. When applied to movers or rotators, the random offsets and angles are rerolled, and then the child object itself is rerolled as well. We developed a prototype showcasing ProGen VR with Unity and an Oculus Rift headset. An interactive menu is shown over the user's non-dominant hand, and besides options to create procedural objects and execute operations, the menu also includes options common in 3D modeling applications such as movement and rotation lock, snapping, and scene scaling. Locomotion is possible by moving around and by teleportation, and objects in the scene do not respond to gravity and do not collide with each other. Also, our prototype supports undo and redo actions. We conducted a user evaluation to both test the prototype's viability and usability and compare our modeling approach with a baseline consisting of the core subset of objects and operations, namely grouping, cloning, deleting, and disbanding objects. In this approach, there are no randomization tools nor tilings available. Participants had to perform 2 tasks consisting of assembling different scenarios from a library of assets with both ProGen VR and the baseline. In the first, participants had to lay out a computer room following a set of requirements, such as there must be exactly 6 desks in the room, each desk must have 1 chair in front of it, 1 computer set, and at least 3 other assets on top of it. The desks should have different sets of items, and the layout of these items must differ. In the second task, participants were given a similar setup with assets to create a town with 6 blocks inside the road skeleton provided. The town had to meet several requirements, such as all 6 blocks must be filled with buildings, all types of buildings must be used across all blocks, the blocks must have different sets of buildings on them, and with ProGen VR, participants were suggested to assemble the unit model first, with all rules defined, and then clone it. We gathered a total of 15 participants, with ages within the interval of 16 to 30 years old, and in both scenarios, participants consistently took longer with ProGen VR. Considering the times to complete the first model of each task, however, it is noticeable that this makes for the most part of the task execution. If we increase the number of required models, this would clearly favor ProGen VR. Indeed, extrapolating the mean time to model of all participants suggests that ProGen VR would be faster than the baseline at approximately 12 desks and 10 blocks for both tasks respectively. After each session, we inquired about task load using a questionnaire with a 5-point Likert scale based on the NASA TLX task load index. This assessment did not vary significantly between the 2 approaches, and the only exception is that the reported physical load in the town center task, which might be related to the extensive repetitive gestures in a larger environment required by the baseline. So, to conclude our presentation, there are difficulties associated with content creation, particularly in virtual reality settings. We proposed an approach for modeling in VR with procedural content generation tools centered around procedural and composite objects. We conducted a user evaluation to compare our approach against the baseline without procedural tools. Results suggest that our approach can be better for complex scenes in terms of time and mental and physical loads. As future work, we are working on making this approach for content creation collaborative, allowing multiple users to contribute for the specification of the rules of a scene. Thank you for your attention. I am now open for questions.
Thank you very much. Yeah, we have a question.
Hello. I have a few questions for you. First of all, the baseline is something that's related to in-VR editor or outside in 2D? The second, would you like to complete all the questions before you ask? And I cannot hear you.
Procedural tools enabled.
Could you please repeat?
The baseline was indeed in VR as well. It was basically the same prototype with the procedural tools disabled.
Okay, so I have 3 remaining questions. One, how how does this compares with the traditional non-in VR, I mean out of VR, creating a 3D scene by hand, let's say, through a 2D editor. The second one is I have only seen flat landscapes where you paint on, let's say. What's going on if we're not on a flat surface? So let's say we want to have a forest in a mountain. And lastly, do you have something like a completely randomizer? Let's say I want to have a brush that paints forests and I want to, let's say, have a density and I want to click somewhere in the map and it will really randomly, in random places, place, let's say, various objects. Many thanks. Sorry for the many questions.
Sorry, I kind of lost it. I forgot the first one when you were saying the third. Can we start one by one, please?
The first one was how does this compares to the traditional creation of a 3D scene via a 2D editor in my laptop, let's say?
We did not actually conduct such evaluation, mainly because those are targeted at different kinds of users, let's say. Maya and Blender and such softwares are more oriented to expert users that have a steep learning curve. We, on the other hand, focused on providing natural interactions that are easy to grasp for the common user. Let's call them that. So the target audiences are a little bit different, and we are focusing on a more easier to learn approach. So, but yes, we did not conduct such evaluation yet.
So the second one is what happens if the surface that you want to put the objects is not flat? Let's say we have a mountain and we want to put a forest on the mountain. Does it automatically, let's say, moves based on the landscape?
We didn't consider that at the moment. We can specify different heights for the objects. So although the videos were shown working on a planar surface, if objects are placed in different heights, the approach works as well. What you are saying implies not only being placed in different heights, but adapting to a terrain that varies in height itself. I'm thinking that if possibly the primitive objects that are the base for our rules know how to deal with that height difference, so we can have some object that automatically fits to the height of the plane in that point, we can apply our rules to such objects, and that will propagate through the hierarchy and apply to such terrain. But we did not consider that scenario extensively, yes, specifically.
Okay, the final question was, do you have, let's say, something like a brush, paint airbrush, I think it's called, where we can randomly, let's say, spread a tree in variations. So instead of doing it manually, creating a grid or etc., we can just completely randomize and have it like a brush, someone painting really quick. I have seen it in my in 2D, it's happening, but I don't know if it's happening in yours case.
Address. I'm sorry, I forgot to wait a little bit for the mic to switch. It is indeed a very common approach. We did not considered it in our initial set of tools. The more close thing to it we have is what we shown, creating a group with several random objects in the middle, and then cloning said group. Now that I'm thinking of it, I think that it would not be much difficult to implement it following our rules. It would have a different set of constraints. But at the moment, we do not have such tool now.
Okay, thank you very much. Some of you may have another question, but it's time to move on. Thank you very much. So let's thank the speaker again.
Very much.
So the last talk of this session is entitled Forecast Real-Time Foveated Rendering and Unicasting for Immersive Remote Telepresence. And this work was conducted by the 3 institutes in Italy. And I think the first speaker, first author, Jonas Theodoros de Ferra, is going to give a talk. Are you ready? Somehow we cannot hear you.
I'm going to present our work
yes.
named Forecast, the real-time foveated rendering and unicasting system for immersive remote telepresence. And then I would like to take some time to explain our motivation for this work. So we always wonder why it's so inherent to our human nature to move from one place to another different place. And if we see the human history, we have been on the move into different places here on Earth and their own space. We have been on the move for different purposes. We moved from a place to place for exploration, communication, share experiences, and most importantly, to help each other. Especially with the rise of modern computing systems and with the ability to transform a physical phenomena into a digital representation, facilitated this inherent human nature. Now, you might be wondering what this part of the human nature has to do with this research, actually. I'm talking about this because it illustrates the importance of going physically beyond our local environment to another one. As I said before, this could be for exploration, collaboration, and to perform critical tasks. And especially this will be very important when there is a need to help each other or visit our families in special occasions. However, moving to an environment that are too dangerous or unreachable to a human being is something we need to give a lot of attention. And environments like this, a physical separation becomes very important. For example, when we see the recent COVID pandemic, we saw that the need for physical separation between patients and healthcare workers. And this could be for testing, laboratory work, or decontamination. And we need to do all of this remotely. In this case, remote telepresence systems became very important. So when we see closely telepresence system, it comprises a telepresence acquisition system, such as a robot, where a human operator controls and see the remote environment through a fast internet communication system. And these days, most of telepresence systems are equipped with sensors, which has the capability to scan the remote environment in 2 and 3 dimensions. All the data acquired are transported through a fast internet communication to a user side that has a high resolution display mechanism without requiring a physical presence. We have seen these kind of technologies in different, let's say, working conditions. So the one on the left, the one that you see is a telepresence systems where they use a robot to do industrial application assembly tasks. The research work showed a success in industrial assembly, but it used a stereoscopic video to display a stereoscopic and monocular videos that created a fixed and non-adaptable camera viewpoints. But instead, the research work in the middle and the right uses point clouds where they can freely move around and see the remote environment. But because they use a 3D data, it creates latency, and there is a low latency that negatively impacts the sense of presence and provoke cyber sickness. We did also an experiment where we do a point cloud-based telepresence system where we attach the 3D sensors on the robot and scanning the environment and visualizing it into a remote station user side. So we measured the latency and the bandwidth, and then we try to see what are the negative impacts of point cloud-based telepresence systems. What we see is point cloud-based telepresence systems are big in size, and they require large bandwidths, and they need high latency transmission. And because of this reaction, 2 changes of the environment became slow. There is a latency, and sometimes it could be non-existent, and eventually negatively impact the situational awareness of the user, and it also creates affect also the sense of presence. So what we observe from our experiment, also from the literature, is these following points. So as we know, the environment is not fully known and perception is incomplete. And there is a huge network latency and throughput limitations. And there is a quality difference between the acquired physical world and the display data. And because of all of these challenges, there is the reaction to changes of the environments became slow, eventually affect the sense of presence and provoke cyber sickness. And nearly all attempts of solving this issue have focused on solving the challenges between the acquisition system in the telepresence components and the communication system in between. And when we see the purpose of such systems, they are designed to allow a human user to immerse into a distant or inaccessible environment. So instead here, we take inspiration from the user, specifically the human visual system, towards designing a new data flow pipeline from sensor data acquisition to its rendering in VR. So when we closely look at the human visual system, it is by far the most important organs of sense is our eye, and we perceive up to 80% of all impressions by means of our sight. And if other senses such as taste or smell stop working, it's the eyes that best protect us from danger. So the objective of this study is to understand the essential perceptual foundation and evolution of the human visual system to design efficient remote visualization interfaces. Most importantly, we will study investigate different visual acuity, the eye physiology to describe it, the human visual system as an optical system. So when we study the human visual system and how vision is possible through our eyes, we can look at the user, and vision perception is possible through photoreceptors that give us color and night vision. There are two photoreceptors cells, rods and cones. And cone receptors are concentrated in the fovea of the eye at 0 degrees centricity, whereas rod receptors are concentrated in a more peripheral retina. And visual acuity is the maximum in the center of the visual field at 0 degrees centricity, whereas it's minimal in the more peripheral areas or retinal regions. And different kind of visual information can be processed in each region. Similarly, in the human brain, retinal vision is mapped in the visual cortex, which is called retinotopic mapping, where neurons within are arranged in an orderly way that preserves the spatial information arriving from the retina. So the other important point that we should study is the visual acuity, commonly referred to as a clarity of vision. It can be quantitatively represented in terms of minimum angle of resolution, or MAR, and can be approximated as a linear function as in the following equations, where MAR0 is the intercept, which signifies the smallest resolvable eccentricity angle for humans, and M is the slope of the linear model, and it is experimentally approximated. The figure shows how visual acuity degrades as a function of eccentricity, and each retinal region has a distinct constant MAR values. So now we understand a little bit of how the human visual system works. Let's see how actually images formed on the retina while we are in the virtual reality displays. So the optical system in head-mounted displays used for VR environments allows light rays to converge and focus on a point on the retina, thus producing virtual images. Since the intention is to project the retinal regions and calculate the radius of each concentric regions, and then the sensitivity values noted in this table can be used to project them. So the radii R for each of n retinal regions are calculated using the tangent of the corresponding eccentricity and scaled by the distance between the virtual image and the lens. So now we saw that like the human vision system does not have a uniform vision across the field of view. So this is very important. So we can ask a very important question: Can we use this human visual system advantage to facilitate a remote visualization system? And the proposed work is focused on this. So the proposed the forecast system framework has an RGBD acquisition system on the remote station, where it converts the depth map and the current information into a point cloud, and it transmits the information through a communication channel to the user, where the user is going to look at. And from the user side, we extract important information such as eccentricity angles, retinal regions, gaze direction, and the head-mounted display positions. Using these informations, formulate them as mathematically as follows, and then transmit all this important information to the remote side to create a replica. Once we have done, now we can project each retinal regions onto the point cloud to partition them into n concentric conical regions as follows. So then we put partitioned regions into a voxel grid with voxel size correlated with the linear Mar relationship we defined in the previous slides. Using the voxel size of the foveal region as the base size, we calculated the next region's voxel size using the linear Mar relationship that we showed before. And then the downsampling of points for foveal regions, we skipped it. This region has the highest visual acuity. It's left-untouched. We don't want to downsample it, but the downsampling in the subsequent peripheral regions is done by approximating the point cloud within each voxel with its 3D centroid. In general, the forecast framework looks like this. So we have three parts where the remote side, where each component that you see on the top here, and the user side has the one that you see on the bottom. So the remote side has components for real-time data acquisition or reconstruction, for raycasting, region selection, sampling, and encoding point clouds, and then transmitting them into the user side where the user is decoding, converting, and then rendering to the user side. So, so this is the video that you can see where we put everything together. As you can see here, as you can see here, the point cloud in the center have high quality, and subsequent peripheral regions have a progressively declined quality according to the human visual system. So the evaluation is therefore carried out both through a quantitative and subjective assessment. The quantitative metrics help objectively evaluate the framework in terms of the amount of data that can be reduced while streaming 3D point cloud data. Also the improvement in data transfer rate, and also the improvement in the end-to-end data transfer rate and latency. And the subjective metrics help us subjectively evaluate the effect of data reduction on the quality of visualization for the user. So we created two conditions that are created to represent 2 inches of the sampling scale: no sampling as a reference, and full sampling to simulate the approach of fully downsampling a point cloud to allow the least streaming cost. 3 test foveated conditions were created, each having a different combination of the 6 retinal regions. 3 datasets were used, and sample images are as follows. And the reduction of points results in degradation of the visual quality on the peripheral regions, especially when rendering to the user. In order to quantitatively evaluate it, a new volumetric-based PSNR metric is proposed, which utilizes 2 volumetric densities for a reference and for the test conditions. So as you can see here, in the experimental result, we see a high PSNR values for the test conditions and the lowest PSNR values for F0. And also we measured the latency and the bandwidth reduction by measuring each component's latency required when we are processing. So for the F0 condition, we see that the latency and bandwidth improvement is more than 70% because it's the lowest sampling. And for the 3 test condition is more than 60% speed up over the reference conditions, which are also statistically significant. And a user study to assess the visual quality of experiences proposed also using the double stimulus impairment scale study approach. Subjects were first presented with a reference condition followed by a 3-second pause and one of the altered condition between F1 and F3 following immediately after in a randomized manner. So the subjects were then asked to rate the second presented stimulus on a 5-point scale. So where we measure the mean opinion score of their rating. So as you can see here, the F0 conditions has the highest score and the F0 conditions has the lowest, which is telling us that it's very annoying, but all the test conditions are scoring more than 3. And the other subjective assessment we wanted to measure is the network latency, throughput, and the throughput limitations. As I mentioned before, because of latency and throughput requirements, reaction to changes of the environment is slow. We designed another experiment setup for where we track a balloon, where we measure the effect of applying the proposed techniques for tracking moving objects. So where we extracted the 3D fixation point and the balloon, and we measured the root mean square error between the balloon trajectory and the gaze direction. And we measured the root mean square error, and then we found F2 compared to others, and F2 reveals a smaller error in trajectory. So with this, I would like to conclude with the following points. And this work showed that there is a significant reduction in bandwidth and latency when we use this system, and it improves the user's quality of experience. And it also created the ability to choose among different conditions or settings based on task and user requirements. Also, it provided innovative way to improve the state-of-the-art in immersive visualization of remote real-time 3D data. Thank you very much for your attention, and I will take your questions now. Thank you.
Thank you very much for the interesting talk. Any questions or comments? No, while we are thinking. So let me start. Yeah, so it looks like a very interesting and smart idea, but it heavily depends on the accuracy of the gaze tracking, right? So so using the current the head-mount display with the eye track card and using the current accuracy of the gaze predictor, so the I don't know how to articulate my question, but how I guess if you can predict the eye direction, I guess perfectly, then your algorithm will work very well. But I'm not sure how the eye tracking with a poor accuracy will degrade your performance.
Definitely. An eye tracker with accuracy, like lower accuracy, that will also totally affect. So it creates actually some kind of aliasing effects, or also not matching the point of fixation. That's true. But the most important thing, as you mentioned, the gaze predictions is very nice actually, especially in remote visualization systems where you can predict where the operator is going to look at. So before the operator, the user, sorry, before the user is going to fix it, you can provide enough information and reduce the latency required actually. So gaze prediction is very important. In the future, I think we would like to also explore that to anticipate where the user is going to look at.
Thank you. Any other questions? Okay, so let me ask another one. So if I understand correctly, basically you render the point clouds, call out the point clouds. But what about the mesh, triangle meshes? So if you want to, to fill the image to connect the vertices with the meshes, then in your approach, you will sometimes have missing surfaces or some fake surfaces or something like that.
This approach can be applied also for mesh, actually. So for this now, we used it for point clouds because there are enough point cloud compression codecs like algorithms. This can be also applied to mesh. Basically, we can downsample a mesh and then stream them based on the human visual system. This can be applied. But in this project, we used a point cloud approach just because there are enough codecs for point cloud compressions.
Okay, thank you very much. No more questions? Okay, so let's thank the speaker again. Thank you very much. So this concludes this session. I'm sorry I didn't read all of the author names and affiliation names to save time, but for more details, please look at the original papers. Thank you very much.
Kyoka Sensei, thank you very much for your sharing. And the next keynote talk session will start at 5 p.m. So yeah, we have a small break in between. And yeah, some of you were seeking drinks. So now we have a coffee service in outside of this conference room. So if you want to, yeah, take that, please grab that one. Yeah, thank you. それでは、ICAT-EGVE2022 の、そうですね、3件目の、基調講演の方に移っていきたいと思います。Thank you for everyone for your participation. And this is the third keynote talk today at the ICAT-EGVE. And this is also a joint keynote talk with SM VRST. And today we have Mr. Daito Manabe as the keynote speaker in this session. And Mr. Manabe graduated Tokyo University of Science, Faculty of Science. And after that, he moved to IAMAS, Media Art School at GIF, Japan. And his media art works can be found in, for example, closing session of Tokyo Olympic. So today, I think we are able to see many technologies behind of his work. 真鍋様、ご講演どうぞよろしくお願いいたします。
真鍋です。よろしくお願いいたします。日本語で話すので、ちょっと通訳の、翻訳の関係上、少しゆっくりめに喋ります。今日はライゾマーティクスというですね、会社、元会社で今グループ名になりましたけど、アーティスト名になりましたけど、を代表して、過去のプロジェクトと、その背景、ビハインドザシーンですね、どういったことが、行われていたかっていうことをちょっと紹介していきたいなと。ページ変わってないね。はい。2006年に設立して、今だいたい50人弱の、全体では、社員がいます。で、主に、エンジニアと、映像クリエイター、デザイナー、デザイナーはプロダクトからウェブから、ユーザーインターフェースから、そして、建築のチームだったり、プロデューサーがいるっていう感じで、いろいろな、メンバーがいる、一つのグループなんですけれども、僕のいるチームは基本的にみんな、コーディングを、するタイプの人たちが多いです。で、僕自身は、バックグラウンドは、大学で数学をやってたことと、あと、音楽活動をやってたことがあるので、そういった、バックグラウンドを活かしながら、このメンバーで、コラボレーションしながら、作品を作っています。で、作品制作の、ほとんどのプロセスは、R&D と、実験ですね。で、これは、今ちょっと見ていただけると分かると思うんですけど、これ、無線で、制御ができる、台車ですね。で、こういったものを、これは開発して初めて、 スタジオで実験をしている時の様子です。なんでまだ、この技術だけがあって、コンテンツはない状態ですね。無線で制御が、できるっていうことを、じゃあこれを使ってどういうパフォーマンスを作るかっていうことは、ここから、考えていって、これ最終的には、こういう感じの、作品になります。ちょっとだけ流しますね。5人のダンサーと、プロジェクター1台と、あとはこの、台車ですね。無線で制御できる台車を使って、作った、ダンスパフォーマンスですね。これだからどうやって作ったって言っても、最初に台車ができた時点では、本当にこういう風になるっていうアイデアは、固まってないんですけど、とにかくいろいろと実験をしながら、振付家と、演出家と一緒に、作っていったっていうようなものですね。で、これはまた他のパフォーマンスで使ったもので、で、さっきの台車ももちろん、モーション、センサー使って、位置と角度を解析してますけど、モーションキャプチャーのシステムを使って行ってます。で、このドローンも同じように、モーションキャプチャーのシステムを使って、ドローンの、位置と姿勢を、解析をして、で、同じく、無線でコントロールをしています。で、これはまだ、初めての実験でちょっと落ちたりしてますけど、こういう振付演出家の、みっこさんがいろいろ何ができるかっていうのを探って、で、これはまた、本番のものですけれども、ダンサー、これも同じく5人ですね。5人のダンサーが、手で光を、操っているような、演出っていうのをステージ上でやりました。はい。で、さっきの台車のシーンで始まって、このドローンの、シーンで終わる、1時間10分ぐらいの、作品なんですけども、どちらも、共通しているのは、最初に、技術ネタができて、で、その後で、ダンサー、振付家、演出家と一緒に、作業して、何ができるかっていうのを、探す。だから R&D の、フェーズがあって、で、その後はそのコンテンツ化をどうやってやるかっていうフェーズを、演出家、振付家と一緒にやるっていうようなことをやってます。で、今日は、できる限り、いろんなプロジェクトを、見てもらいたいなと思うので、あんまり会社の話はちょっとこれ以上せずに、具体的な、作品の紹介をしていきたいなと思います。で、一つ目、これちょっと長いプロジェクトだったんですけど、2013年から2021年、これ厳密にはまだこの先もあるかもしれないですけど、去年が一応今のところ最後で、フェンシングのビジュアライズと、フェンシングの剣先を可視化するっていうようなプロジェクトをやったものです。で、これは一番最初に、ハイスピードカメラ1000フレーム、1秒間に1000フレームで撮影したフェンシングの、練習の風景なんですけれども、これ、見ていただけるとわかるように、1000フレームも、必要なくて、で、この後、300フレームぐらい、あれば、剣先が、取れるっていうことが分かったので、最初は、剣先を、モーションキャプチャーのカメラで剣先にマーカーをつけて、トラッキングするっていうアイディアを作って、でもちろん本番の試合では使えないんですけど、その、技術を、アイディアを使うことでフェンシングの試合がより面白くなるんじゃないかっていうことで、提案したものになります。これ 剣先にマーカーがついてますし、選手はモーションキャプチャーのスーツを、着ているので、姿勢も、剣先も、容易に、検出できるんですけど、この時、2013年で、ここから課題が始まってですね、なんとかマーカレスで剣先を検出できないかっていうことで、プロジェクトがスタートしました。で、2013年、14年時点だとですね、まだまだ全然、剣先が機械学習技術を使って取るっていうことは難しかったんですけれども、2018年あたりに、リアルタイムでマーカレスで剣先を検出することができるようになりました。で2019年には、カメラダイスシステムをアップデートして、3D で、トラッキングができるようになって、本番の試合でも使ってもらえるようになりました。で、ちょっと前半の、まだまだ完成する前のものですけれども、これは、かなりシンプルな、画像解析の、アルゴリズムで剣先を、見つけようとして、実験している様子ですね。ただ、かなり理想的な環境であったとしても、そんなに精度は出ないと。それはやはり、剣先がかなり小さいっていうことが、一つ、原因としてはあります。で、剣もしなるので、これがずっとしならなければ、剣先を予測することは、簡単なタスクだと思うんですけど、剣先もしなる。試合になると選手と、影になるとか、そういったこともあるので、より複雑になっていくというような課題がありました。で、CNN、コンボリューショナルニューラルネットワーク、を使って、解析をすること、機械学習技術の進化で、アルゴリズムを変えたことによって、検索が徐々に取れるようになってきたっていう、のが2017、18年ぐらいですかね。この時はもうマーカレスでかなり取れるように、なってきたと。で、これ2019年で、これは初めて試合で実際に使った様子になりますね。なんで、2013年にスタートして、そこから、6年かけて、最終的に、本当の試合で使ってもらえるようになって、最終的に、東京オリンピックでも、使っていただけるところまで、到達しました。これが、ちょっとオリンピックの動画ではないんですけど、2019年の動画ですね。で、この時は、2D だけじゃなくて 3D で、剣先を検出しているということになります。で、ポーズ、人のポーズの推定も、行っているので、選手の、体を 3D 化して、でもちろん剣先と剣の形も取っているので、普段では絶対見ることのできない視点から剣先の動きを見るというようなこともやりました。で、もちろん、画像のデータを、その学習データを作るところっていうのが、一番、機械学習が大変になるところだと思うんですけれども、この時は選手の方にお手伝いいただいて、カメラ8台で、選手が12名で、バックグラウンドは理想的な環境ばかりだと、なかなかいろんなところで対応できないので、ライトの、環境を変えたりとか、後ろの背景を変えたりとかっていうことをやって、で合計で、20万枚以上の、画像に、手動でラベリングをしていったという感じですね。はい。なんで、この作業が非常にボリュームが大きかったという感じです。で、剣先の検出に関してはですね、ヨロというアルゴリズムを使ってますけれども、ライブラリを使ってますけれども、最初にまず剣先じゃなくて剣を見つけて、そこから剣先を見つけるっていう ふうにですね、タスクを2つに分けています。で、システムは、こちらですね。ちょっとこれは細かく話すと、時間かかるんで、ちょっと簡単に説明すると、カメラは24台あって、で、全部のカメラで、検索を、見つけに行くと、時間がかかる、計算コストが無駄にかかるので、選手がいるエリアっていうのを、ライダーで検出をして、で、一回そこで、選手のいるざっくりした位置がわかるので、で、それで、解析にかけるカメラを指定して、そこから解析をして、その結果を、映像のグラフィックを生成するマシンに送信をして、で、合成して出力するっていうようなことを、AR で出力してっていうようなことをやっています。なんで、リアルタイムといっても、そんな、カメラで、なんですかね、数フレームとかっていうレベルではなくて、数秒かかる感じですけれども、かなり、フェンシングの試合では、プレイバックの時に使うので、その要件には満たしていたという感じです。はい、で、これは一つの事例で、その次が、リオの、2016年、東京2020オリンピックフラッグハンドオーバーですね、リオオリンピックの、ちょっとご覧いただきますね。
東京からリレーされたボールが赤く光って、東京とリオがつながりました。
そしてスタジオが暗くなりました。浮かび上がったのは東京オリンピックで実施される33の競技のアニメーションです。
正式に実施競技となった野球、ソフトボール、空手、スポーツクライミング、サーフィン、スケートボードなども表示されています。
AR 拡張現実というデジタル技術で CG と現実世界を融合させています。
2022年にはこうした技術を使って新たなスポーツ中継が行われるかもしれません。光を放つフレームが、
はい。で、これはもう本当かなり大きなチームで制作をしていたので、ちょっとここで全部上げることは難しいんですけど、僕が担当してたのは今、マリオが出てきてから後のシーンで、最初の AR のシーンだったり、あとこの光るフレームとか床面の映像とかっていうのを、担当しました。で、この振り付けとかもちろん演出とかっていうのは、この時はみきこさんっていう振り付け家がやって、あとは、本当にディレクターチーム、プロデューサーチームもすごくたくさんの方たちがいたので、正確なクレジット、ちょっとウェブサイトとかをご覧いただきたいんですけども、ちょっと自分たちが担当していたところだけ少し、紹介したいと思います。で、これも、プロトタイプとか、プラクティスっていうところが非常に重要になるんですけれども、このスタジアム規模で、実験できる機会っていうのは、もちろんとても限られているので、最初は、こういった、スタジアムでイベントが、自分たちのやりたい演出をやらせていただける機会を見つけて、で、まずは無線のテストを兼ねて、こういう光のデバイスを作って、実際の現場で実証実験する。というようなことを、やりました。で、これは光のパターンが、SD カードの中に入っていて、で、実際に通信しているのは光のパターンではなくて、最初のトリガーだけ、再生の Q だけを 920MHz で、送信しています。で、もちろん無線なので、バックアップを持つ必要があるんですけど、そのバックアップっていうのは、最初にあるタイミングでダンサーさんが押して、一応その時点で Q は走っていて、光のパターンは始まっていて、で、その後に無線でもう一度、信号、再生の Q を送ると。なんで、無線の Q を受けたらより正確なタイミングで走るけど、万が一無線を受けなかったとしても、手動の Q が走ってるので、光らないっていうことはないっていうようなバックアップでやってました。で、これは本当に地元の北海道でやったものなんですけれども、地元のダンサーに集まってもらって、ちょっとこういう無線のデバイスを使った、ちょっと実験 的なというか、まあ、その実証実験としてやらせていただいたような感じですね。で、それ以外に最初の、AR と言われていたシーンがありますけれども、まあ、これなんか自分たち、ライゾマティクスの中では、シームレスミックスドリアリティっていうような呼び方をしているんですけれども、まあ、AR と、VR、いわゆる CG の世界っていうのを、リアルと VR の、CG のカメラの情報を、位置とか角度とかレンズとかを合わせることで、シームレスに行ったり来たりできる。そういうような、演出を、まとめてシームレスミックスリアリティっていう風な呼び方してるんですけど、それを最初に、この前からやってるんですけども、結構うまく、プロジェクトとして見せられたのがこのパフォーマンスで、Perfume がサウスバイサウスウェストでやったパフォーマンスです。で、これは僕らが、映像分の、制作をやって、演出とか、実はこの映像のコンテとかも、みっこさん、振り付け演出家の方がやってますけど、この辺ですね。これ今 CG に行って、現実世界に行って、CG に行って、で、この後またカメラが現実世界のカメラの位置に戻って、生のカメラに切り替わると。でもちろんこれ録画というか、事後処理だったらいろんなやり方があると思うんですけど、リアルタイムで配信でやっていたので、全部リアルタイムの処理をする必要が、ありました。技術的には、そうですね。カメラ、モーションキャプチャーのカメラが天井につってあって、で、このそれぞれのパネルに、上にマーカーがついていて、パネルの位置を、トラッキングをしています。ちょっとこの話をするとこれだけで終わっちゃうんで、これはさっきのリオのオリンピックの AR の、技術の、そうですね。デモとして作ったわけじゃないですけど、やっぱこれがすごくインパクトがあったので、こういった演出に近い、そういうシームレスな現実と VR の世界を行ったり来たりするような、演出を、リオでもやろうということで、待ってですね。で、その後これはビョーク、のライブの映像ですけど、これも、同じように、この時はキネクトを使ってすごくシステム的にはシンプルにやってますけれども、リアルな、さっき言ったそのシームレスミックスリアリティの演出っていうのを、やりました。なんでこの辺は別にデモとしてやってるわけじゃないですけれども、技術的なことだったりとか、演出の考え方とかっていうのは、近かったので、参考にしながらやってます。で、あとは、これはもうちょっとそのハード寄りの話ですけれども、ハードももちろんプロトタイプを、たくさん作ってます。で、最終的な、LED の数とかそういうのを決める前に、果たしてフレームで、こういう LED のフレームを作って面白くなるかで、どれぐらいのサイズだったら持てるかとか、どれぐらいのサイズが必要か、その演出的にっていうのを試すためにも、本当にすごく簡易的なプロトタイプを作って、で、ちょっとサイズを決めたりとか、そういう実験をしていました。ね、これはボツになった演出ですけど、なんかこれセグウェイ使ったものとかも、いくつか考えてですね。あとはもちろんこういうデジタルで、とかハードでやるっていう、実寸でやるっていうのもありますけれども、もちろんこういう小さなオブジェクトと、紙とか鉛筆とかで、ブレスト的にいろいろと検証することもありますし、もちろんスケッチも、たくさんしました。で、あとは、最終的にこのプロジェクトで一番うまくいったのは 3D のソフトウェアで、いろいろシミュレーションしたことでした。で、シミュレーションが必要だったのは、もちろん、みんなでイメージ共有するっていうためもあるんですけれども、そもそもこの リオのフィールド上では一度もリハーサルができないっていうことがもう決まっていたので、なんで、まず最初に、現場に行って、スキャンをして、で、もちろん、図面とかもあるんですけど、図面よりもスキャンした方が正確なので、このスキャンのデータを手がかりに、いろんなことを決めていきました。あとはカメラの位置を、AR で、これは、なんで、その実際のカメラの位置から、一回 CG のカメラに移って、で、また実写のカメラに移ってみたいなことで、CG のカメラのムーブメントの、検証用に、行ってたちょっと動画ですね。で、これ実際にさっきの AR の演出の時にこういったカメラの動きになってます。あとはこれは、オープンフレームワークス、オープン GL のツールキットを使って、制作したシミュレーター兼、あとは、これ自体で、映像を書き出したりとか、ライトのパターンを書き出したりとかっていうようなことをやってます。で、これを正確に作ったというか、これのツールを作るのにかなり時間をかけたんですけども、そこがすごく、うまくいった要因かなという気がしています。でもちろんこれ、僕はすごくこのプロジェクトで面白いなと思ったのは、このキューブ自体今動いてますけれども、これ最終的には人力で人が動かして、行ってるんですけど、こういう CG で作った、これプレビズと言われる、シミュレーションを、人間の力を使って実現するっていう、そういったコンセプト自体もすごく面白いなと、思いましたね。あとはもうちょっとリハーサルも、完璧なものはできないので、こういう原っぱで、プロジェクターを使うコストもかけられなかったので、AR で合成をして、みんなで練習し終わった後に、AR で映像合成して、こういう風に見えるはずだから、みんなこういう風に動こうとかっていうことを、やってましたね。あと、ドローンを使ってとかっていうのももちろん、いましたと。ね、これも、そのプロジェクターのコストを頑張って削ることがどれぐらい全体の予算に対してインパクトがあるのかちょっとわからなかったんですけど、我々はとにかく予算をかけないっていうことはかなり優先順位が高い話だったので、このプロジェクターではなくて AR でずっと最後までやってっていう感じですね。あとは、それ作詞の演出が、ありまして、で、これを聞いている皆さんはそういったことすごい詳しいと思うんですけど、ここの、床面に反射している絵は、これプロジェクターの光なんですね。なのでよく見ると土管にちょっとプロジェクターの絵が被っちゃっていて、これはマスクが事前にできなかったのでしょうがないんですけど。なんでこの、もちろんこれはこのカメラの方向から、位置のあたりからしかこういうふうには見えないんですけれども、このフレームの光と、床面の映像を、合わせることで、水面のような、効果を、出せると。もちろんこれは東京は水の都っていう、コンセプトも当時ありましてですね。そういったことから、水面っぽい質感というか仕上がりを作ったんですけども、これももちろんカメラのいろんなカメラから自由に撮られてしまうと全く成立しないので、これは放送局に送った、カメラの指示書ですね。ここはAR で、実はここは我々のパソコンから映像がブロードキャストされてたので、カメラのスイッチングのシステムを全部自分たちのものを使ってたので、指示書はないんですけど、ここからですね、これ今右の方に camera 1 or 2, only use cam 1 and 2, switch between cam 1 to optical illusion image will be on the floor って書いてますけど、まあ、こういう作詞が、まあ、1か2でしか成立しないから、ちょっと気をつけてね、みたいなことをちょっとお願いしたりとか。っていうのはまあ、これはカメラのスイッチングが自分たちで全部はやらせてもらえないので、まあ、放送局側に、お願いをするっていうようなことをやりました。まあ、それ以外にもずっと指示が最後まで入ってますけれども、まあ、こういう AR とか作詞とか、まあ、カメラワークとかがまあ肝になるので、まあ、そういった指示もしましたですね。で、まあ、ライブの本番の、AR のアプリなんですけれども、この AR でやるんですけど、まあ、カメラにマーカーをつけてトラッキングしてとかっていうこともできないですし、カメラにセンサーを取り付けることもまあできないので、まあどうしたかって、しかもまあ3時間前までカメラの位置と角度、正確な位置と角度がわからないっていう条件だったので、まあどうしたかっていうと、ちょっと、まあこういった CG 側を、まあ最終的に実際に設置されたカメラの位置と角度に合わせていく必要があるので、まあそのために、まあガイドをちょっと、この時は LED のスクリーンをまあガイドにしてますけど、そういったガイドを使って、微調整をするっていうようなことをやってます。これは、まあ実際のカメラを使う前に、スタジアムの、まあ、iPhone で撮影したデータを使って、まあこんな風にできるはずだっていうのをちょっとやったものです。あと、これは、スティッチングの、まあ、シーケンスのテストをやってるものですね。はい、であと、まあ、当日の本当ギリギリにポジションをちょっと微調整するためのツールっていうのも、まあ、用意をしてやっています。この辺は、まあ、シーケンサー、まあ、結構、自分たちのプロジェクトだと多いんですけど、まあ、本当に細かく、Q を打ち込むので、照明のソフトとかではなくて音楽ソフトで、打ち込んで、まあ、照明を制御するということをやってます。結構これも面白いなと思うんですけれども、その VR、まあ、CG、まあ、シミュレーションの世界ではまあ見える、パターン、例えばこの先に、こういう簡単な波紋みたいなものっていうのがパターンであって、で、このパターンが、そのダンサーが動かしている光のデバイスを通じてちょっと見えてくるっていうところもすごく面白いなと思いました。この全体のパターン自体は、こういう、すごいシンプルなソフトで作ってますけれども、コンセプトとしては、こういう目に見えないものが、こういう映像を通じて見えるんではなくて、光のフレームっていう結構プリミティブな形状のデバイスを通じて見えてくるっていうところがまあ面白いポイントですね。あとは、なんか、だいたいマックスでやってますっていう話ですね。まあ、あとこういう、まあ、我々がやるものっていうのはなんか、シミュレーションでは結構簡単にできるんですけれども、これが実際の、まあ、現実に落ちてくるとすごい大変っていう、まあ、さっきの光のフレームとかもそうですけど、これはOKGO っていう、バンドのミュージックビデオで、これもシミュレーション上では、まあ簡単っていうかシンプルなもんですけど、実際にやるのはすごく大変だったミュージックビデオです。ちょっとこれ最初の方だけ流します。
looks so quick, moving so slight, could almost imagine it didn't just happen. But everything will change in just one little glance. It's not passing fascination now, it's obsession. It's obsession. It's obsession.
まあ、見ていただけるとわかると思うんですけど、まあ、プリンターを使った、コマ撮り動画っていう感じですね。で、まあ、一番遅いところで32分の1のスピードで動いていて、まあ、一番速いところはまあ実写のスピードですね。なんで、シーンによって、結構、コマ撮りのフレームが違うんですけれども、まあ、最初から最後まで、まあ、プリンターを使って、プリンターでパラパラ映像を作るっていうのが、まあ、コンセプトで作り切った、動画です。で、この、まあ、アイデア自体は、6っていう広告代理店と、あとこのバンドの、まあ、バンドマスターダミアンっていう、今、前に登場した、まあ、彼が、作って、で、まあ、我々はそれをじゃあどうやって実現するかっていうことを、お手伝いしました。まあ、これ YouTube にもある。まあ、これも、ちょっとさっき言ってたみたいな、その作詞のシーンですね。ある角度から見ると、奥行きがある映像に見えるっていうのを、まあ、プリンターでやったっていう感じです。で、これも、YouTube にあるんで、まあ、興味のある方は後で見ていただけたらと思うんですけど、まあ、こういうシミュレーションのアプリを、まあ、作って、まあ、制御するっていうようなことをやってます。まあ、結構その場でこれ嬉しそうにしますけど、割と現場に行くまでなんかわかんないこともたくさんあったので。っていうのと、まあ一発勝負なので、やっぱりそのシミュレーション通りに、できないと大変なことになるので、かなり事前の、テストとかっていうのはたくさんやりました。で、これ本当に一番最初に試した時の、動画で、まあ最初はちょっとちっちゃい規模で、もう単純に白い紙が出るだけの、テストっていうのをやりました。これは撮影した映像の2倍の速度で、再生するっていうようなことをやったですね。これ16倍。これが16。これか。なんでまあ、ここで実際に、そもそも面白いのか、このアイディアはっていう、その技術的にはもちろんできるのはまあ分かったとして、面白くなるのかっていうような検証をここで、やってます。これはまあライゾマティクスのオフィスで、やってたんですけど。これは実際32分の1倍で、動いて撮影して、その後32倍して再生するってことをやった実験ですね。ごめんなさい、32倍じゃん、16倍でした、16倍。はい。まあ、もちろんその後、まあ、映像、プロジェクターでできる。まあ、あとはもう、見栄えとかサイズ何台必要かとかっていうのは、まあ、プリンターじゃなくてプロジェクターを使って、まあ、必要な台数とかを、まあ、決めていったっていう感じですね。結構、まあ、こういうのも、まあ、さっきのリオのやつとかも、まあ、VR で、実際に観客席から見たらどういう風になるかみたいなソフトを作って、まあ、実験とかもやったんですけど、まあ、やっぱその肉眼でスケールを確認する必要っていうのは、まあ、いつでも 出てくるかなっていうところですかね。このウィンターの時も、もちろん、かなりいろんなシミュレーションっていうのをやったんですけど、例えば、
this paper, how will we...
この辺が、まあ、いわゆるプレビズっていうやつですね。
All of this is...
なんで、何枚目の紙が、どのタイミングで出るとか、まあそういったこととかを、まあ事前に決めてやってるっていう感じですね。まあこれもなんでシミュレーションが、非常に必要なプロジェクトでした。で、あと、まあちょっと次のプロジェクトもこれシミュレーションネタなんですけれども、これはアイルトン・セナっていう F1 レーサー、もう今から30年近く前に、まあ、大活躍していたレーサーですけれども、まあ、彼が走った時のそのテレメトリーデータ、まあ、データが、走行データが残っていて、でそのデータを、その紙をデータに変換して、で、そのデータを使って、鈴鹿サーキットにセナが蘇ったような、ことをやるっていうプロジェクトでした。はい。でも、ホンダの CM だった、広告のプロジェクトだったんですけど、僕は、主に、紙のデータを、デジタルデータに変換する部分と、あとそのデータでシミュレーションをするっていうことと、あとこの、ライトが置かれてますけど、このライトを使うっていう、まあ、アイディアとかっていうのを、あと実装をやりました。これもね、すごく昔のプロジェクトなので、まあ、今の方は知らないかもしれないですけど、当時すごく話題になったプロジェクトで、まあ、こういった紙のデータを、まず、デジタルデータに変換をして、でシミュレーターの、アプリで、まあ、ライトをどれぐらい置くべきなのかとか、出して、ですね、これもまあ、やっぱり最初は、全部プロジェクションマッピングでやりたいとかっていうアイディアとかを出されて、で僕はプロジェクションだとそもそもお金がはまらないし、まあライトで、やるぐらいがポエティックでいいと思うっていうことで、まあ提案をして、それが通ったんですけど、で、これは、そうですね、ライトが、合計で6535個、まあ必要なプランで、最終的にはもうかなり減って、300いくつまで減ってますけど、っていうようなことをやりました。まあ、これシミュレーションで、まあその後また今度実寸で、シミュレーションをやるっていう感じですね。なんでまあ、当倍のサイズではもちろんできないですけど、ちょっとちっちゃいサイズで、実際に、これ面白くなるのかどうかっていうことを、シミュレーションでやった後に、実際のスケールでやるっていうことをやりました。そもそもその時速300キロとかで走ってたりするので、まあその感覚がどれぐらい必要かとか、そういう検証ですね。はい。これ実際に、テストしてたところですね。なんでまあもちろん、ね、これが、映像で、プロジェクションでやっても、まあ良かったのかもしれないですけど、こういうプリミティブな光の表現をすることで、まあ見てる人が、まあ、想像できる余地もあるし、まあそもそもそれぐらいのことで、なんか良かったんじゃないかなっていうのを終わった後も思いました。まあこれもまあ同じくカメラの、レイアウトとかをして、はい。まあこれは実際に、本当に設置してるんで結構大変な 設置よりも撤収の方が大変だったっていう、大雨が降ったので。ね。はい。あともう一個ぐらいなんか、紹介。じゃあちょっとこれも、じゃあこれもちょっと日本だと見てる方も多いかもしれないですけど、これも広告の、プロジェクトで、ドコモのプロジェクトで、3カ所に分かれて、東京、ロンドン、ニューヨークの3カ所に分かれてライブをして、で、速い通信環境で映像と音声を、送って、合成をして、で、ライブとしてお届けするっていうのをリアルタイムでやるっていう、プロジェクトでした。で、これ本当にやってるんですけど、僕はニューヨークに行ったんですけど、4K の、ちょっと 4K の映像と、2チャンネルの音声を、もちろんこれ遅延があるんですけど、我々がやった時には1秒の固定の遅延で、映像を、送受信するっていうようなことをやりました。なんで1秒間の遅延があるので、ロンドンと、ニューヨークの映像を東京に送って、東京で合成して配信するっていうようなことをやってるんですけど、なので東京は、その、1秒の遅延分、早く踊ってるということですね。で、これ、なんかリモートとかになる前のプロジェクトですけど、なんですかね。すごい、そのコロナの後にこういういろんな場所から映像を、ズームとかでもそうですけど、送って、なんかライブやるみたいなのありましたけど、これはそういう3カ所で分かれてライブをやってるんですけど、できるだけ1カ所でやってるように、見せるっていうことを、工夫した、プロジェクトですね。なんで各会場に16台ずつカメラが置いてあって、で、そのカメラのスイッチングのタイミングっていうのを3カ所全部、同じようにしているので、もちろんカメラの位置と角度も合わせて、スイッチングをすると。で、そのワイプ、このプロジェクトで一番工夫したところはワイプなんですね。で、この 3D の情報を使って、映像をワイプするっていうようなことをやっています。なんで、よくあるワイプだと、その 2D のワイプ、2D 的なワイプが多いと思うんですけど、そうではなくて、同じ場所に、あたかもいるように見せるために、この 3D の、それぞれの会場の建物の 3D の情報と、あとこの、三角錐の、3D の情報を使って、で、さらにこの3人の、スキャンの、モーキャップの情報もあるので、そのモーキャップの情報もうまく使いながら、ワイプを考えたっていう感じです。このワイプもなんかね、いいネーミングとかすればよかったんですけど、スピンバーンちょっと。で、これももちろんですね、同じようにシミュレーションが必要で、まず3箇所の同じようにスキャンをしに行って、3D のモデルを取るっていうことと、あとこのワイプも果たして面白いアイディアなのかどうかっていうのをちょっと最初3人の 3D モデル、踊りが入る前に一回ちょっと試して、で、結構うまくいきそうだっていうことになり、ちょっとずつ先に進んでいくっていう。で、今度はその、振り付けがもう出来上がった段階で、 このワイプっていうのを、より振り付けと連動したものにしていくっていう作業をします。なんで、ワイプのアイディアとかそういったテクニカル的な演出をやってる間に、振り付けとか、ダンスとかっていうところは同時並行でやってもらってるという感じですね。これ多分2ヶ月ぐらいで、企画をどういうことできますかっていう相談が来てから完成まで多分2ヶ月ぐらいでやったような気がするんですけど。この辺はちょっとずつ本番に近づけていくっていう。で、あと、そうですね。この時はちょっとシンクのことも結構シビアな問題だったので、どれぐらい、ニューヨークと東京でこれはシンクができるかっていうテストをやったものでした。そうですね。なんでこれもちょっとまだまだ、いろいろとお見せしたい資料とかもあるんですけど、ちょっと今日は50分までということだったので、一旦ここまでにしたいと思います。なんでどれもシミュレーションをかなりたくさんやって、実現しているっていうところが、ですかね。なんでしょう。AR とか VR とかっていうのも、それ自体がコンテンツになることもありますけれども、我々は、それもやりますけど、結構こういうシミュレーションとかにかなり、そういった、アイディアを使っていることが多いっていうです。はい。で、ちょっと質疑応答の時間をというお話を伺ってたんですけど、どうでしたっけ？どのように進めればよろしいでしょうか？
はい、ありがとうございます。それではZoom 経由で質疑を会場の方から質問出させていただくという形でよろしいでしょうか。
私は、はい、何でも大丈夫です。
So, if you have any question, please raise your hand. We can ask via Zoom. So, I think, yeah, you can ask in English, then we try to translate. Okay,
please. ちょっと日本語で、いきます。普通の研究活動の、すごい離れて、いい活躍だと思いました。特に面白かったのは光のフレームが、多分トラッキングがついてなかったんですね。そのダンサーによって、角度とかタイミング、かなり多分難しかったので、それもちょっと、追加に説明していただきたいんですけど、発表ありがとうございます。
とにかくこれは練習をしてるっていうこともあるんですけど、あと例えばこういう床面に映像を出すっていうことが、演出にもなるし、あとはこの映像自体がガイドにもなるので、なんで結構この演出のために映像を出してるっていう意味合いと、あとはこのフレームが正確に動かせるようにとか、正確な場所に置けるようにするために、映像を出すっていう、二つの意味合いがありますね。なんで、この下に映像が出てれば、結構そのフレームを映像のタイミングと同じように動かせるので、合わせやすいと思うんですけど、これ映像がないよりもあった方が、精度も上がるし、あと、結構ところどころこれすごくよく見ると、本当に印のため、フレームを正確に動かすためだけのために出してる映像とかっていうの結構あるって感じですね。これとかそうか。 そうですね。この辺とかも、その床面の映像とフレームの位置をとにかく正確に合わせて出したいんですけど、実際よく見ると結構ずれてたりもするんですよね。フレームを置いたところから波紋が出るっていう風にやろうとしてるけど、うまくいってないところもあって、で、やっぱりうまくいったの気づいて、ちょっとずつ直していって、で、最後、この形に持っていくっていう。なんで、その演出っていう意味とガイドっていう意味が、その床面の映像には2つ入ってたっていうことですかね。
ありがとうございます。Thank you for the answer.
奈良先端大の清川と申します。非常に面白かったです。いろいろな取り組み見させていただいたんですけども、技術的にまだちょっとハードルが高いんだけど、ぜひやりたいと思っているような、例えばスポーツだとか、なんかそういう動きってありますか？今ちょうどできるかできないか。
トラッキングっていうことですかね、意味。
はい、はい。
なんかそのフェンシングの、例えばサッカーとか野球とかピンポンとかって、やっぱボールを探すっていうタスクは、なんか実は意外と、剣先に比べると簡単だったなっていう気がしていて、で、フェンシングの剣先を見つけるっていうのはなかなか手強いタスクだったなという感じがしています。で、今、そうですね、なんか、スポーツで、なんかやってみたいっていうのは、どっちかっていうと、スポーツっていうよりもそのボール上のものを、コントロールして、新しい表現をするとか、なんか結構その地上の演出、ドローンとかは割ともうやり尽くされてるので、その地上で動くそういう軍ロボットみたいなことだったりとか、なんかそういう方法には興味ありますけど、スポーツの解析で今パッと思いつくのは、ちょっとないですね。ちょっとスケーターとかもやりましたけど、でも全然、簡単なアルゴリズムでできちゃうので。
なんか我々実は、スイミングのトラッキングに取り込もうとしていて、相当難しいなと思ってるところなんですけど、で水中と水上と両方あって、なんか泡が立ったりだとか、普通のトラッキングシステムが使えないんですよね。でシンクロナイズとかもプロジェクションでなんか演出すると、なんかそういうトラッキングをリアルタイムにすることにお取り組みの中で結構相性がいいのかなと思ったんですけど、水泳とか難しそうだなと思っていて、そのあたりなんかコメントとかありますか？
なんかそうですね。ちょっと最後までやりきれてなかったですけど、確かに、水の中の、その水泳のトラッキングみたいのは、なんかちょっと一回だけやったことありますね。でも、モーキャップ使ってたんで、あんま大した、そういう技術的な障壁は、その時なかったですけど、でも、そのマーカレスで、なんか、いろいろ解析して演出するっていうのは、すごい面白そうなので、やってみたいですけど、やってみたいって言って、できるもんでもないんですけど、チャンスがあればやってみたいですね。
ありがとうございます。
Okay, please go ahead.
I especially liked the very last project. I think I missed the title of that project. Could you remind me what the name is in case there's more information on it online? Thank you.
こちらの最後のプロジェクトの名前をぜひ非常に面白かったので知りたいというふうに質問でございました。
You can find the project with searching Docomo and perfume, I guess.
Is there any other question, comment? はい、 非常にリアルとバーチャルの両方の要素というのをすごくうまく組み合わせて使っていらっしゃるというのが非常に印象的なお話で、大変すごいスケールだなというのを改めて感嘆いたしておりました。ちなみにこういった場合にどの要素をリアルにしてどの要素をバーチャルにするのかというところ、真鍋様の考えている理想的な組み合わせみたいなものとかセレクションの基準みたいなものがもしありましたら伺えたらありがたく存じます。
これはなんか僕の個人の多分表現の話ですけど、やっぱり人間がいないとリアルに感じない、ステージ上とかだと、それは CG とかそういうことではなくて、例えばロボットショーとか、ドローンショーとかももちろん手掛けたこともありますけど、やっぱそこに人がいて、その人とインタラクションすることで、リアリティというよりも自分事として見られるっていう感じなんですかね、お客さんが。なんで、やっぱインタラクション、人とのインタラクションをどういうふうに入れていくかみたいなところはいつも考えてますね。だからこれとかも別に、ドローンショーとしてももちろん、これちょっとね、数が少ないんであれですけど、成立もするとは思うんですけど、やっぱこの人の動きを使ってドローンをコントロールしてるっていうところで、なんか面白さが出てるのかなっていう気がしますね。で、実際にこのドローンのライトがダンサーに当てられて、そのダンサーの存在感がちょっとドローンによって強調されるみたいなことだったりとかっていう感じですかね。
ありがとうございます。I was asking about selection queue to make a virtual element and real element, and Manabe-san is saying that to have human is very important to make a presence or a reality for the media contents. So that is a key point of his thinking. 他いかがでしょうか。Do you have any comment or question? はい、それでは真鍋様、非常にたくさんの作品のコンテンツとそのバックグラウンドをお話しいただきましてありがとうございました。真鍋様、thank you so much for Mr. Manabe to have such a great presentation of the content and also technical background. So we very much appreciate and enjoyed your talk. Thank you so much.
Thank you very much. ありがとうございました。
ありがとうございました。それでは真鍋様、以上で本日のご講演終了という形で終わりにさせていただければと考えております。本当に遠隔のコンディションの中貴重なお話いただきましてありがとうございました。
Thank you very much.
So, yeah. So the oral session of today's conference is over. So yeah, next event will be welcome reception for you. So I hope you can participate this one. And the time of the welcome reception is 6:30. So you have 20 to 25 minutes to before starting that session. So you can stay here for a while, something like 10 to 15 minutes, and then you can go to the venue of welcome reception by walking. That is just inside of our university. So, and the student volunteers will be able to guide you. So yeah, if you want to participate, welcome reception, please stay in this room. Okay, thank you very much for your participation. Let's conclude this session.